Hello there, and welcome to Physics with William, where curiosity settles in quietly, science takes off its shoes at the door, and the universe is allowed to explain itself at a comfortable pace. Tonight, we are turning toward one of the most familiar forces in existence, and also one of the least understood: gravity. It is the thing that keeps your feet on the floor, keeps the moon circling the Earth, keeps the Earth circling the Sun, and keeps your cup of tea from floating away in a very inconvenient and frankly rather rude manner. Gravity is everywhere. It shapes galaxies, bends light, gathers stars, pulls oceans into tides, and gives every object with mass a quiet influence over every other object. And yet, when physicists try to describe it using the language of the smallest things in nature, something important seems to be missing. A particle, a tiny messenger, a quantum hint, a little packet of gravitational influence that has been given a name, though it has never been seen. The Graviton. Before we drift into that mystery, I would love to know where you're listening from tonight, and what time it is in your part of the world. Are you hearing this near midnight, when the room is still and the clock has begun to sound louder than usual? Are you listening in the early evening, with the day not quite finished, or perhaps in the morning, which would make this a rather unusual but very respectable breakfast with gravity? It is a nice thought, really. People in different places, under different skies, all being held gently to the surface of the same planet by the same invisible force, all thinking about the same missing particle. If you find this kind of calm journey through physics soothing, or if it helps your thoughts slow down after a long day, I would be very grateful if you liked the video and subscribed. It helps this little corner of quiet science reach others who might also enjoy falling asleep while learning why the universe is so deeply strange. Now, the graviton is not an object you can picture easily. It is not like a little metal ball or a grain of sand or a speck of dust glowing somewhere in space. Particles in modern physics are not tiny marbles, even though we often talk about them that way because our brains like things we can imagine with fingers and tables and biscuits. A particle is more like a small excitation of an underlying field. That may sound rather grand, but the idea can be approached gently. Think of the surface of a pond. If the pond is still, nothing much seems to be happening. But toss in a pebble and ripples move across the water. The ripple is not a separate thing from the pond. It is the pond moving in a particular way. In quantum physics, particles are often understood a little like that. They are ripples in fields. The electron is a ripple in the electron field. The photon, the particle of light, is a ripple in the electromagnetic field. And if gravity has a quantum field of its own, then the graviton would be the smallest possible ripple of that gravitational field. That is the basic idea, though basic in this case means we have only opened the front door and noticed that the house is bigger on the inside. The graviton is often called the missing particle of gravity, because in the great collection of particles that physicists use to describe nature, gravity does not yet fit comfortably. We have a very successful quantum description of the other known fundamental forces. Electromagnetism has photons, the strong nuclear force has gluons, the weak nuclear force has heavy messenger particles with rather unromantic names that sound more like catalogue labels than characters in a cosmic story. These particles help us describe how forces act between matter at tiny scales. They are not little workers carrying notes in tiny envelopes, but that image is not entirely useless. In a loose way, force-carrying particles are how fields communicate changes and interactions. They are the means by which one piece of matter can affect another through the rules of quantum theory. Gravity, however, has always been the difficult relative at the family dinner. It behaves beautifully on large scales. It explains falling apples, orbiting planets, collapsing stars, and the great web of galaxies. Thanks to Einstein, we do not usually describe gravity as a force pulling across space in the old sense. Instead, we describe it as the bending of spacetime itself. Matter and energy tell spacetime how to curve, and curved spacetime tells matter how to move. That description has been tested again and again, and it works astonishingly well. It predicts the bending of starlight around the sun. It explains the shifting orbit of Mercury. It tells us why clocks tick at slightly different rates depending on gravity. It even predicted gravitational waves, those tiny stretching and squeezing disturbances in space-time that were finally detected after travelling across the cosmos from colliding black holes. Einstein gave us gravity as geometry, not a tug, but a shape. And then quantum theory gave us another view of nature, one that works with almost unbelievable accuracy in the world of atoms and particles. Quantum theory says that the small world is not smooth and definite in the way everyday objects seem to be. It is probabilistic, restless and grainy in certain ways. Energy comes in packets. Fields fluctuate. Empty space is not truly empty. Particles can appear as possibilities, interact, vanish, and leave measurable effects behind. This quantum description is not optional. It is the most successful framework we have for the microscopic world. It explains chemistry, lasers, computer chips, nuclear reactions, and the behaviour of the matter that makes up your body. It is strange, yes, but it is strange in a way that keeps being correct, which is the most irritating kind of strange if you were hoping for a simpler universe. The problem is that general relativity and quantum theory do not naturally speak the same language. General relativity treats space-time as smooth and flexible. Quantum theory treats fields and interactions as uncertain and quantized. When physicists try to make gravity quantum in the same way as the other forces, they are led toward the idea of the graviton. If gravity can be described by a quantum field, then its influence should come in little quanta. Those quantas would be gravitons. In that sense, the graviton is not just a random particle invented because physicists had an empty shelf and wanted to complete the set. It is what many approaches suggest should exist if gravity is brought into the quantum world. But there is a complication, and it is a large one. Gravity is incredibly weak compared with the other forces. That may sound odd because gravity feels very important. Drop your phone, and gravity wins immediately, usually against the phone. Jump into the air and gravity brings you back down without asking your opinion. The entire Earth pulls on you every moment, but that is the key. It takes the entire Earth to create the pull you feel as weight. A small magnet can lift a paperclip against the gravitational pull of the whole planet. Electromagnetism, at small scales, is vastly stronger than gravity. Gravity only becomes dominant when enormous amounts of matter gather together, because it always attracts, and because large objects contain huge numbers of particles. On the scale of single particles, gravity is so feeble that detecting one individual quantum of it becomes almost absurdly difficult. This is why the graviton sits in a strange place in science. It is not wild fantasy. It is not simply a science fiction decoration placed on the dashboard of a spaceship. It is a serious theoretical idea. Many physicists think that if gravity has a quantum description, gravitons should appear in some form, and yet, detecting a single graviton may be beyond any experiment we can realistically build. The universe may contain gravitons everywhere, passing through you, through the room, through the Earth, through distant galaxies, with almost no chance of interacting in a way that could be caught. They would be quieter than quiet, more elusive than neutrinos, and neutrinos are already famous for treating entire planets as if they were made of mist. Trying to catch a graviton would be like trying to hear one snowflake land during a thunderstorm, except the snowflake barely touches the ground, and the thunderstorm is the entire universe being noisy. That is part of the charm of the question. What a graviton really is depends on how gravity and quantum mechanics ultimately fit together, and that is still one of the great unfinished tasks of physics. We have pieces of the puzzle that work beautifully on their own. We have Einstein describing the large-scale structure of space-time. We have quantum field theory describing the behaviour of particles and forces. We have experiments that confirm both with astonishing precision in their own domains. But when we ask what happens at the heart of a black hole, or at the first moments of the early universe, or at distances so tiny that space-time itself may no longer behave smoothly, the pieces begin to strain. It is as if we have two wonderful maps of the same country, one showing mountains and rivers, the other showing streets and houses, but when we try to lay them over each other, the coastlines do not quite match. The graviton, then, is a clue. It is a signpost pointing toward quantum gravity, the deeper theory that would describe gravity without leaving quantum mechanics outside in the rain. We do not yet know what that theory will look like. It might resemble ordinary quantum field theory in some ways. It might require strings, loops, holographic ideas, emergent space-time, or something no one has yet named because the person who will name it is currently somewhere doing homework and unaware of their future responsibilities. But whatever the final theory turns out to be, it must explain why gravity behaves the way it does, why space-time curves, why black holes have thermodynamic properties, and how the smooth geometry of Einstein emerges from a universe that may be quantum underneath. One gentle way to begin is to remember that gravity was mysterious long before the graviton was imagined. For ancient people, gravity was not separated out as a universal law. Heavy things fell because that was their nature, or because they belonged to the earth, or because the world had a proper order. Then Newton arrived and gave gravity a mathematical form. He showed that the same influence pulling an apple downward also keeps the moon in orbit. That was a remarkable unification. It meant the heavens and the earth followed the same rules. The sky was not a separate kingdom made of perfect motions and divine machinery. It was part of the same physical world as orchards, tides, and dropped sandwiches. Newton did not explain what gravity was in a deeper mechanical sense, but he described how it worked with extraordinary power. He gave us gravity as universal attraction. Einstein later changed the picture again. Gravity was not a force acting instantly across empty space. It was the curvature of space-time. The sun does not pull Earth with invisible strings. The sun changes the geometry around it, and Earth follows the straightest possible path through that curved geometry. It is straight in space-time, even though to us it looks like an orbit. This idea is difficult at first because our everyday experience does not include flexible space-time. Kitchen floors do not visibly curve when you place a melon on them, unless something has gone structurally wrong and you should perhaps call someone. But mathematically and experimentally, Einstein's picture has been extraordinarily successful. It turned gravity from a mysterious pull into the shape of reality itself. Then quantum physics made the question sharper. If every other force has a quantum description, what about gravity? If light comes in photons, might gravitational waves come in gravitons? A gravitational wave, in Einstein's theory, is a ripple in space-time produced by accelerating masses, especially enormous events like colliding black holes or neutron stars. Such waves have been detected as tiny changes in distance, far smaller than anything our ordinary senses could notice. In a quantum view, just as an electromagnetic wave can be thought of as made of many photons, a gravitational wave might be thought of as made of many gravitons. But the waves we detect are classical in practice, meaning they involve vast numbers of possible quanta acting together. Detecting the whole wave is hard enough. Detecting one graviton inside it would be another matter entirely, rather like hearing an entire orchestra from far away, and then trying to identify the vibration of a single violin string while sitting on another planet. Still, the word graviton is useful because it gives us a way to ask precise questions. What properties would this particle have? It would have no mass, as far as standard expectations go, because gravity reaches across unlimited distances, and massless force carriers are associated with long-range forces. It would travel at the speed of light, because changes in gravity propagate at that speed according to relativity. It would have a particular kind of spin, known verbally as spin 2, which is connected to the way gravity affects space-time and matter. That detail matters because different force carriers have different spins, and spin shapes the mathematical behaviour of the force. But we do not need to write formulas to appreciate the broad point. A graviton would not simply be another particle in a list. Its properties would encode the fact that gravity is tied to spacetime itself. That makes it more subtle than the photon. A photon moves through spacetime and carries electromagnetic influence. A graviton, if it exists in the usual sense, would be a quantum ripple of the gravitational field, and the gravitational field is not just something sitting inside spacetime. In general relativity, gravity is spacetime geometry, so the graviton seems to be a particle associated with the quantum behaviour of the stage itself. It is not merely an actor walking across the stage, it is a tiny tremor in the floorboards, the lighting, the distance between the seats, and perhaps even the timing of the performance. That is why gravity is hard to quantize. We are not only quantizing a field in space, we may be trying to quantize the structure that tells us what space and time are. This is where the topic becomes both scientific and humbling. The graviton is a reasonable expectation, but it is also a reminder that our current language may be incomplete. Sometimes science advances by finding the thing it predicted. Other times it advances by discovering that the prediction was a shadow of something deeper. The atom was once imagined as indivisible. Then it turned out to contain electrons, protons and neutrons. Protons and neutrons then turned out to contain quarks and gluons. Light was once debated as wave or particle, and now we understand it as something that refuses to fit neatly into either everyday category. The graviton may be similar. It may be discovered as a particle in a future theory. Or it may be replaced by a more subtle idea, where gravity emerges from quantum information, or from entanglement, or from structures we do not yet know how to picture. For now, the graviton remains missing not because it is ignored, but because it is almost impossibly shy. Physics has a long history of chasing invisible things. Neptune was predicted from the wobble of Uranus before it was seen. Neutrinos were proposed to explain missing energy before they were detected. The Higgs boson was predicted decades before experiments found it. In each case, theory pointed towards something hidden, and experiment eventually caught up. The graviton belongs to that tradition, but with a warning label attached. The weakness of gravity makes the experimental challenge so extreme that some physicists argue a single graviton may never be directly detected by any practical device. Not because we lack patience, but because a detector sensitive enough to catch one might have to be so massive that it would collapse into a black hole, which is the universe's rather firm way of saying please stop. And yet, we continue. Not always by trying to catch a graviton directly, but by looking for clues. We study gravitational waves, we study black holes, we study the cosmic microwave background, the faint afterglow of the early universe. We study particle physics, quantum information, and the mathematics of space-time. We ask whether gravity behaves differently at tiny distances. We ask whether black holes destroy information or preserve it in strange ways. We ask whether space-time is fundamental or emerges from something deeper. The graviton sits quietly inside many of these questions, like a missing word in a sentence that still almost makes sense. So tonight, as we begin this slow exploration, the graviton is our guide into a deeper mystery. It is the proposed particle of gravity, but also a symbol of the gap between the physics of the very large and the physics of the very small. It asks us to think about why objects fall, why planets orbit, why light bends near massive bodies, and why the universe seems to have rules that are both beautifully consistent and stubbornly incomplete. It asks us to consider whether space-time is smooth or grainy, whether gravity is geometry or a quantum field, and whether those two descriptions might turn out to be different views of the same underlying truth. For the moment, there is no need to rush toward the hardest questions. We can start with the simple fact that gravity is the most familiar mystery in your life. You have felt it every second since you were born. You feel it now in the weight of your body, in the pressure of a blanket, in the way the chair supports you, in the way a tired hand rests on a table. It is constant enough to be taken for granted and strange enough to occupy the best minds in physics for centuries. Somewhere between the falling apple, the curved path of starlight, the collision of black holes, and the imagined whisper of a graviton, there is a story about how nature holds itself together. And to understand why a missing particle matters so much, it helps to go back to the older picture first, to the time when gravity was not yet a ripple, not yet geometry, not yet quantum, but a force that seemed to reach across the darkness and quietly pull the moon around the Earth. Gravity first appears to us as something very ordinary. It is the reason a spoon falls from the edge of a table, the reason your pillow stays on the bed, the reason rain comes down instead of wandering sideways with the confidence of a confused pigeon. It is so constant that we rarely notice it unless it suddenly becomes inconvenient. A dropped phone, a tripped foot, a heavy suitcase lifted one stair too many. In daily life, gravity feels like the background rule that everything quietly obeys. Yet the more carefully we look at it, the less ordinary it becomes. This familiar downward pull is also the force that gathers gas into stars, holds planets in their paths, shapes the tides, bends light around galaxies, and decides the fate of entire regions of the universe. It is not just something beneath us, it is above us, around us, inside every orbit, every falling object, every drifting cloud of cosmic dust. Gravity is the hand that holds the cosmos together, though it has no fingers, no rope, no visible machinery, and no obvious explanation that satisfies every scale of nature at once. The easiest place to begin is with the feeling of weight. When you sit in a chair, you feel supported because the earth is pulling you downward and the chair is pushing upward. Your body interprets this as pressure, heaviness, contact. You might think of gravity as the earth tugging on you, and for many purposes that is a perfectly useful way to speak. The earth has mass, you have mass, and the two of you attract each other. The pull on you is strong enough to keep you from drifting away into the sky, which is helpful if you enjoy breakfast at ground level. But the attraction goes both ways. You pull on the earth too. The difference is that Earth is so enormously massive compared with you that its motion in response is too tiny to matter in ordinary terms. When you jump, Earth technically moves toward you by an amount so small that even the most dramatic jumper cannot take much credit for planetary motion. Still, the mutual nature of gravity is important. Gravity is not only something large objects do to small ones, it is something all mass and energy do to each other. This universality is one of gravity's most remarkable features. Every piece of matter contributes. A stone, a tree, a mountain, a person, a planet, a star. Each has gravitational influence, however tiny. Even the cup beside you is attracting you, and you are attracting it. Fortunately, the pull between everyday objects is so weak that your tea does not slide across the table toward you unless there are other forces involved, such as a slanted surface, a clumsy elbow, or a cat with scientific ambitions. Gravity is always there, but most small things do not have enough mass for their pull to be noticeable. This is why gravity seems to belong to planets and stars. It is not because they have a special kind of gravity, it is because they contain enough matter for the tiny contributions to add up into something grand. That adding up is what makes gravity the architect of the large-scale universe. On small scales, other forces can dominate. Electromagnetism holds atoms and molecules together, gives structure to materials, powers chemistry, creates light, and allows your hand to press against a table instead of passing through it. The nuclear forces govern the interior of atomic nuclei and the reactions that make stars shine. Gravity is much weaker than these forces when individual particles are involved, but it has one great advantage. It always attracts in ordinary circumstances, and it has an unlimited reach. Electric charges can cancel because positive and negative charges balance one another. Large objects are usually electrically neutral overall. Gravity has no such simple cancellation for ordinary matter. Mass does not come in positive and negative types that cancel out the way electric charge can. So, as more matter gathers, gravity grows in importance. A planet is not held together by glue, nails, or cosmic enthusiasm. It is held together because every bit of it pulls on every other bit. This is why loose matter in space does not remain loose forever if it is dense enough and cold enough. Clouds of gas and dust can slowly gather under their own gravity. At first, the motion may be gentle, almost hesitant, like dust drifting in a sunbeam. But as material clumps together, the gravitational pull strengthens. More material falls inward. The center grows denser and hotter. Given enough mass, a star can be born. The glow of a star is not caused by gravity alone, but gravity makes the conditions possible. It squeezes the star's core until nuclear reactions can begin. Then, a long balance follows. Gravity tries to pull the star inward, while the energy produced in the core pushes outward. For much of a star's life, it exists in this balance, neither collapsing completely nor exploding apart. It is a vast sphere held in a delicate argument between inward pull and outward pressure. A star is not simply burning in space. It is gravity and light negotiating for millions or billions of years. The same principle shapes planets. Around young stars, disks of gas and dust rotate, and within those disks, particles collide, stick, gather, and grow. Gravity gradually helps small clumps become larger clumps, and larger clumps become worlds. The early stages are messy. Objects crash into each other. Some merge, some shatter, some are thrown away. The solar system did not form as a tidy display model. It formed through collisions, heat, leftovers, and time. Gravity sorted much of the chaos into orbits. It helped gather the sun at the center, planets around it, moons around planets, and smaller bodies in belts and distant reservoirs. Even now, the solar system is a gravitational arrangement, a long-running dance in which each body affects the others. The sun dominates because it contains most of the mass, but Jupiter tugs, Saturn tugs, Earth tugs, and everything participates in the shared motion. The result is not perfect clockwork, but it is stable enough that calendars can be made, eclipses can be predicted, and astronomers can sound impressively calm while discussing objects moving at enormous speeds. An orbit is one of the loveliest consequences of gravity, though it is often misunderstood. A planet does not orbit because gravity has stopped pulling it. Gravity is pulling it all the time. The planet is continually falling toward the sun, but it also has sideways motion. Because of that sideways motion, it keeps missing. This is a strange but useful way to think about orbiting. The Earth is falling around the sun, always drawn inward, always moving forward, always missing the center because its motion carries it along a curved path. The Moon does the same around Earth. Satellites do the same when we place them high enough and fast enough. They are not free from gravity. They are falling with style, which is also how some people describe getting out of bed too quickly, though the physics is less elegant. This idea helps explain why astronauts in orbit appear weightless. They have not escaped Earth's gravity. Earth's gravity is still strong at the height of the International Space Station. The astronauts and the station are both falling around Earth together. Since everything nearby falls at nearly the same rate, there is no floor pushing up on the astronauts in the usual way. They float because they are in continuous free fall. The word weightless can be a little misleading, because gravity has not vanished. The sensation of weight is mostly the sensation of support, the push of the ground, chair, floor, or mattress resisting gravity. Remove that support during free fall, and the body feels weightless. This is why a brief drop in an elevator gives that little stomach-lifting sensation. For a moment, your body and the elevator are both moving downward together, and your ordinary sense of weight changes. It is a small reminder that weight is not exactly the same thing as mass. Mass belongs to the amount of matter and energy in you. Weight depends on gravity and support. A bathroom scale is not judging your essence. It is measuring how hard the earth and the floor are involved in your morning. Gravity also gives us tides. The moon pulls on Earth, and because the side of Earth nearer the moon feels a slightly stronger pull than the far side, the oceans respond. The result is a stretching effect, a raising of water into tidal bulges. The sun contributes too, and the shapes of coastlines, ocean basins, and local geography make real tides wonderfully complicated. But the basic cause is gravitational difference across Earth's width. Tides are not just the moon pulling water upward in a simple lump. They are the result of changing gravitational influence across an extended body. The Earth itself is affected as well, not only the oceans. Land rises and falls slightly too, though not in a way that usually interrupts dinner. Tides remind us that gravity is not only about downward falling. It can stretch, squeeze, heat, and reshape worlds. That stretching can be dramatic elsewhere. Some moons around giant planets are needed by tidal forces. As they orbit, gravity from the planet and other moons flexes their interiors. This can create heat. In some cases, tidal heating helps maintain subsurface oceans or drives volcanic activity. A moon can be warmed not primarily by sunlight, but by the repeated squeezing of gravity. That is a remarkable thought. Gravity is usually imagined as cold and distant, the silent force of space. But in the right setting, it can warm the interior of a world. It can stir geology. It can help create environments that may be important for the possibility of life. The invisible hand does not only hold, sometimes it needs. On the larger scales, gravity becomes the organizer of cosmic structure. After the early universe expanded and cooled, tiny differences in density became important. Regions with a little more matter had slightly stronger gravity. They attracted more matter, becoming denser still. Over immense stretches of time, this process helped form galaxies and clusters of galaxies. The universe became a web, with great strands and knots of matter separated by vast emptier regions. Gravity amplified the small unevenness into grand architecture. When we look at galaxies, we are seeing gravity's patience. Stars gathered by the billions, gas drawn into spiral arms, dark matter, whatever its deeper nature may be, shaping the gravitational scaffolding around luminous matter. A galaxy is not a solid object, of course. It is a vast system of stars, gas, dust, and unseen mass moving under mutual gravity. It has structure because gravity gives motion a long memory. The mention of dark matter brings another important point. When astronomers study the motions of stars in galaxies and galaxies in clusters, they find that visible matter does not provide enough gravity to explain what they observe. Something unseen appears to contribute additional gravitational influence. We call it dark matter, not because it is necessarily mysterious in a theatrical sense, but because it does not emit or absorb light in the ordinary ways that would make it visible through telescopes. Its presence is inferred through gravity. This is one of the clearest examples of gravity acting as a detective's clue. We cannot see the dark matter directly in the usual way, but we see its effects in motion, lensing, and structure. Gravity tells us something is there. It does not yet tell us exactly what it is. The universe, being polite but not overly helpful, leaves us with evidence and no label on the jar. Gravity can also bend light. This seems strange at first because light has no ordinary rest mass. Yet in Einstein's description, gravity is not simply a force pulling massive things. It is the curvature of spacetime, and light follows paths shaped by that curvature. When light passes near a massive object, such as a star, galaxy, or cluster of galaxies, its path can bend. This effect is called gravitational lensing. Sometimes it produces distorted arcs, multiple images of the same distant object, or magnified views of galaxies far behind massive foreground structures. Nature, in this way, provides telescopes made of gravity. They are not polished or conveniently adjustable, and they do not come with a user manual, but they allow astronomers to study objects that would otherwise be too faint or distant. Gravity changes not only where matter goes, but how the universe appears. The bending of light also hints at why gravity is deeper than the simple idea of pulling. If gravity were only a tug between masses, light would be awkward to explain. But if mass and energy shape space-time, then even light must respond, because light travels through space-time. This is one reason Einstein's view was so powerful. It made gravity universal in a new way. Nothing with a path through space-time is entirely outside gravity's influence. Not planets, not clocks, not light itself. Time is affected too. Clocks run differently depending on gravitational conditions. A clock closer to a massive body ticks more slowly compared with one farther away. On Earth this effect is tiny, but it is real and measurable. It matters for technologies such as satellite navigation, where precise timing is essential. Your phone's ability to locate you depends partly on accounting for the fact that time does not pass at exactly the same rate everywhere in Earth's gravitational field. That is a very advanced way for the universe to help you find a coffee shop. Still, in ordinary life, gravity feels steady. You wake up with it, walk under it, pour tea in it, and go to sleep while it keeps the bed and the floor in a reliable relationship. This steadiness can hide how dynamic gravity really is. Massive objects move, stars orbit in galaxies, black holes merge, neutron stars spiral together. When enormous masses accelerate, they can send ripples through space-time. These ripples are gravitational waves. By the time such waves reach Earth from distant cosmic collisions, their effect is incredibly tiny. Detectors measure changes far smaller than anything we can sense, yet those measurements have opened a new way of observing the universe. Instead of seeing light from cosmic events, we can feel, in a very precise scientific sense, the trembling of space-time itself. Gravity is no longer only inferred from orbits and motions. It can be listened to through instruments that notice the faint stretching and squeezing left behind by some of the most violent events in existence. Black holes show gravity at its most extreme. A black hole forms when mass is compressed into a region so dense that, within a boundary called the event horizon, nothing can escape outward, not even light. This does not mean a black hole is a cosmic vacuum cleaner roaming around with bad manners. From far away, its gravity can behave like the gravity of any other object with the same mass. If the Sun were somehow replaced by a black hole of the same mass, which is not something the Sun is planning, Earth would continue orbiting in much the same way, though the lack of sunlight would create other problems rather quickly. What makes a black hole extraordinary is the concentration of mass and the structure of space-time near it. Close enough, gravity becomes so intense that ordinary intuition fails. Time, space, and escape all change their meaning. Black holes matter to the Graviton story because they sit at the boundary of our understanding. General relativity describes them with great success, but quantum theory cannot be ignored forever. Black holes have temperature. They appear to have entropy. They can slowly lose energy through quantum effects. These facts suggest that gravity, thermodynamics, and quantum mechanics are connected in deep ways. If a graviton exists as the quantum of gravity, black holes should in some sense involve gravitons, yet the full description remains unfinished. Black holes are like locked doors in physics. We can measure the shape of the door, hear sounds from behind it, and read some of the writing on the frame, but the key is still being made. It is tempting to imagine gravity as a substance or invisible fluid filling space, but that picture can mislead us. Gravity is better understood through effects and relationships. It tells matter how to move. It links distant objects. It creates structure from initial unevenness. It resists being screened or blocked. You cannot put up a gravity shield in the way you might block light with a curtain. If gravity could be easily blocked, the universe would behave very differently, and architects would have had a much stranger job. Because gravity passes through matter and acts across distance, it connects everything in a way that is both gentle and relentless. Every object participates in the gravitational conversation, though most voices are too quiet to hear alone. That quietness is important. Gravity is both the weakest familiar force at small scales and the ruler of the cosmos at large scales. This strange combination explains why it took so long for humans to understand it mathematically, and why it remains hard to merge with quantum theory. We can measure electromagnetic effects between tiny particles. We can build machines that reveal the behavior of the nuclear forces. But the gravitational pull between individual particles is so small that it is drowned out by almost everything else. A stray vibration, a bit of electric charge, a passing truck, thermal motion, the quiet impatience of the laboratory building itself. Gravity hides at small scales not because it is absent, but because it whispers beneath louder forces, and yet, without that whisper, there would be no stars, no planets, no galaxies, and no comfortable downward direction for slippers beside the bed. Gravity turns scattered matter into worlds. It provides the long-term stability that lets planets orbit stars for billions of years. It creates pressure inside stars, making the elements that later become rocks, oceans, atmospheres, and living things. Many of the atoms in your body were formed in stars or stellar explosions, and gravity helped make those stars possible. In that sense, gravity is involved not only in where you're sitting, but in why there is a you to sit there. It is not sentimental to say this, only literal in a cosmic way. The history of matter becoming complex passes through gravity's patient work. When physicists ask what gravity really is, they are not asking because gravity is unfamiliar. They are asking because familiarity is not the same as understanding. Everyone experiences time, but time is still mysterious. Everyone sees light, but light led to quantum theory and relativity. Everyone feels gravity, but gravity points toward the deepest conflict in modern physics. On one side, it is geometry, the shape of space-time. On the other, if nature is quantum all the way down, gravity should have quantum behavior too. The graviton enters here as a possible missing piece. If the electromagnetic field has photons, and if gravitational waves are ripples that can be quantized, then perhaps gravity has gravitons. But because gravity is so weak at the level of particles, and because space-time itself may be part of what must be quantized, the graviton is not just another entry in a particle catalogue. It is tied to the question of whether the stage of the universe has its own smallest motions. Before getting to that smaller world, it helps to appreciate the scale of what gravity already does without invoking any particle at all. It keeps the moon close enough to raise tides and light the night. It holds the atmosphere around Earth, allowing air to remain instead of drifting away into space. It guides comets back from the cold outskirts of the solar system. It shapes the life cycles of stars, from birth in gas clouds to quiet, fading, or violent death. It gathers galaxies into clusters and bends the path of light across billions of years. It slows time near massive bodies and carries news of black hole collisions across the universe as gravitational waves. For something so weak between individual particles, it has an impressive resume. If gravity had a business card, it would need very small writing. There is also something democratic about gravity. It does not care about composition in the way many other forces do. A wooden ball and a metal ball fall the same way in a vacuum if other effects are removed. This equality of falling is central to the path that led Einstein to general relativity. Gravity acts on all forms of energy and matter, and objects in free fall follow paths determined by space-time. The result is that falling can feel like the absence of gravity, even though gravity is the cause of the motion. This is one of those ideas that sounds contradictory until it becomes clear, and then it becomes quietly beautiful. A falling object is not being pressed by gravity in the way a hand presses clay. It is following the natural path available to it in curved space-time. The feeling of weight comes when something prevents that free fall. The ground is what makes gravity feel like a force pressing through your feet. So gravity, the invisible hand, is not always a hand in the simple sense. Sometimes it is the shape of the path. Sometimes it is the balance inside a star. Sometimes it is the stretching of oceans. Sometimes it is a lens made from a galaxy cluster. Sometimes it is a wave crossing space after two black holes have merged far away and long ago. The same phenomenon appears differently depending on where we look. That is why it has inspired so many descriptions, from Newton's universal attraction to Einstein's curved spacetime to the possible quantum language of gravitons. Each description captures something real, each works best at certain scales, and each leaves us wanting the next layer. For now, the important thing is that gravity is not merely a downward pull. It is the large-scale organizer of the universe, the reason scattered matter becomes structure, the reason cosmic history has shapes rather than only mist. It is weak but persistent, quiet but cumulative, familiar but still unfinished. You can feel it right now as stillness, as weight, as contact with the surface beneath you. At the same time, it is guiding the moon, shaping the sun, bending distant light, and holding galaxies in vast rotating forms. The same gravity that makes a dropped biscuit land sadly on the floor also helps build the cosmic web. That range is almost ridiculous, which is probably why physics keeps returning to it with fresh questions. And once we see gravity in that broader way, the next step becomes natural. For centuries, the question was how this invisible influence reaches across space and why it follows such reliable patterns. Newton gave the first great answer, describing gravity as a universal attraction that could explain both falling objects and orbiting worlds. Then Einstein changed the meaning of the answer, showing that gravity was not simply a pull through space, but a change in the shape of space and time themselves. To understand why the graviton is such a difficult missing particle, we need to walk through that shift carefully, from the apple and the moon to the curved fabric of space-time, where gravity stops looking like an ordinary force and begins to look like the geometry of reality. For a long time, gravity seemed easiest to understand as a pull. That word is simple, familiar, and useful. You pull a drawer open, a dog pulls on a lead, a tired person pulls a blanket closer and quietly decides that morning is an unreasonable invention. So when we see an apple fall, a stone drop, or rain descend from the clouds, it feels natural to say that Earth is pulling things downward. For everyday life, this description works well enough. It tells us what to expect. Let go of the spoon, and the spoon will not politely ask whether it may remain in the air. It falls. Throw a ball upward, and after a moment of brief optimism, it comes back. The world appears to be filled with objects being drawn toward one another, and for centuries the great task was to describe that drawing with enough precision to connect the falling apple to the moving moon. Isaac Newton gave humanity one of the most powerful versions of that idea. He did not merely say that things fall. People had known that for quite some time, usually after dropping something breakable. Newton showed that the same rule could apply both on Earth and in the heavens. That was the astonishing part. Before him, many thinkers had treated the sky as a different kind of place, governed by different principles. The Earth was the realm of heavy bodies, falling objects, friction, dust, carts, weather, and other untidy matters. The heavens were imagined by many as orderly and almost separate, filled with perfect circular motions or divine arrangements. Newton helped erase that boundary. He showed that the moon stays near Earth for the same basic reason an apple falls from a tree. The moon is falling too, but because it has sideways motion, it keeps missing Earth. It is falling around us, endlessly, gracefully, and with much better timing than most of us manage when walking into a room and forgetting why we came in. The strength of Newton's idea was not just that it was elegant, it worked. It allowed scientists to calculate planetary motion with remarkable success. It explained tides, it connected projectiles, pendulums, orbits, and falling bodies under one broad framework. It made the universe seem lawful in a new way. Nature was not a collection of disconnected habits. It had rules that could be written clearly, tested, and used. Newton's gravity said that every object with mass attracts every other object with mass. The attraction depends on how much mass the objects have and how far apart they are. We do not need to write the mathematical rule here to understand the picture. More mass means stronger attraction. More distance means weaker attraction. The result is a universe in which everything is quietly tugging on everything else. There is something deeply satisfying about that vision. It gives gravity a kind of directness. The sun pulls on Earth. Earth pulls on the moon. Earth pulls on you. You pull on Earth, though Earth remains unimpressed because it is very large and has had a long day. In Newton's picture, space is like an empty stage, and time ticks onward everywhere in the same steady way. Objects move across this stage, influenced by forces. Gravity is one such force, acting between masses. The stage itself does not bend, stretch, ripple, or take part in the performance. It simply provides the background against which everything happens. That view was so successful that it shaped science for more than 2 centuries. It helped build astronomy, engineering, navigation, and the mechanical worldview of the modern age. Yet even in Newton's own time, there was a question hidden inside the success. How does gravity actually act across empty space? If the sun pulls on Earth, what carries that pull? Is there an invisible rope? Is there some medium filling space? Does the influence travel instantly? Newton was cautious about this. He described gravity mathematically, but he did not claim to know its deep mechanism. That restraint is worth admiring. It is tempting when a theory works well to pretend that it explains everything. Newton knew the difference between describing how gravity behaves and explaining what gravity is. His equations gave the universe a working grammar, but the meaning behind the words was still not complete. For most ordinary purposes, that incompleteness did not matter. Newtonian gravity was accurate enough to predict the motion of planets and the paths of cannonballs. It guided ships and calendars and eventually spacecraft calculations in many practical settings. Even today, engineers and astronomers use Newton's approximation whenever the speeds are not too high and gravity is not too intense. If you are planning a bridge, a building, or the arc of a tossed biscuit, Einstein is usually not required at the table. Newton works beautifully in the middle-sized world of human experience. But nature has a way of hiding its deeper corrections in places where ordinary intuition begins to fail. Very fast motion, very strong gravity, very precise measurement. Over time, small mismatches began to matter. One famous mismatch involved the planet Mercury. Mercury orbits closest to the Sun, where the Sun's gravity is strongest among the planets. Its orbit slowly shifts over time. Most of that shift can be explained by the gravitational influence of the other planets, but not all of it. A small leftover remained, a tiny discrepancy between prediction and observation. It was not large enough to throw astronomy into chaos, but it was persistent. Science pays attention to persistent leftovers. They are like crumbs on a clean table. Something has happened, and the universe is not tidying up after itself. Newton's theory was not failing everywhere, but near the Sun, in the orbit of Mercury, it was not quite complete. Another clue came from the nature of light and motion. By the late 19th century, physics had developed a powerful understanding of electricity, magnetism, and light. Experiments suggested that the speed of light behaved in a very strange way. It did not simply add to or subtract from the motion of the observer in the way everyday speeds do. If you walk forward on a moving train, your speed relative to the ground depends on both your walking and the train's motion. That feels obvious. But light refused to behave like a polite passenger on a train. Its speed appeared to be the same for observers regardless of their own motion. This created a deep problem for the older view of space and time. If space and time were absolute, as Newton had assumed, then light should not behave this way. Albert Einstein entered this problem not by adding one small patch to the old picture, but by changing the foundations. In his special theory of relativity, he argued that the speed of light is the same for all observers moving steadily relative to one another, and that the laws of physics are the same for them as well. To make that work, space and time could no longer be absolute and separate. Measurements of length and time depend on motion. Moving clocks can tick differently from stationary ones, from a given observer's point of view. Events that seem simultaneous to one observer may not seem simultaneous to another. This was not merely a new opinion about clocks, it was a new structure for reality. Space and time were woven together into spacetime. Special relativity did not fully explain gravity, but it changed the setting in which gravity had to be understood. Newton's gravitational influence seemed to act instantly across distance. If the sun were somehow moved, the old picture appeared to suggest that Earth would respond immediately. But relativity said that no influence should travel faster than light. Gravity needed to respect that limit. It could not be an instant message sent across the cosmos with no delivery time. Einstein spent years searching for a deeper theory of gravity that would fit the new space-time view. The result was general relativity, published in the early 20th century, and it changed gravity from a force into geometry. The core idea is often summarized in a simple way. Matter and energy shape space-time, and shaped space-time guides the motion of matter and energy. That sentence sounds tidy, but it carries an enormous change in meaning. In Newton's picture, Earth orbits the Sun because the Sun pulls on Earth through space. In Einstein's picture, the Sun changes the geometry of space-time around it, and Earth follows the natural path through that curved geometry. Earth is not being yanked by an invisible rope. It is moving as freely as possible through a space-time that is not flat. The orbit is the result of geometry. A common image is a heavy ball placed on a stretched rubber sheet, with smaller balls rolling around it. The heavy ball creates a dip, and the smaller balls curve as they move. This picture can help at first, but it is also limited. It uses ordinary gravity to explain gravity, because the heavy ball dips downward due to Earth's pull. Real space-time curvature is not a dip into some extra downward direction, in the same simple sense. It is a change in the relationships between distances, durations, and paths. Still, the rubber sheet image gives a rough feeling for the idea that motion can curve, because the background is not flat. The key point is that in general relativity, space-time is active. It is not a stage that remains unchanged while the actors move. The stage itself responds. This explains why gravity affects light. In Newton's older picture, light had no ordinary mass, so its relation to gravity was not straightforward. In Einstein's view, light follows paths through space-time, and if space-time is curved, the path of light can curve too. This led to one of the great early tests of general relativity. During a solar eclipse, astronomers could observe stars appearing near the sun's edge, where the sun's gravity should bend their light. The measured bending agreed with Einstein's prediction more closely than with the older expectation. The result made Einstein famous and gave the world a new way to picture gravity. Light itself, the fastest thing in nature, followed the curves of space-time. General relativity also explained Mercury's stubborn orbital shift. The region near the Sun is curved in a way that Newton's theory only approximates. When the fuller space-time geometry is used, Mercury's motion comes out correctly. A small leftover became a sign of a deeper theory. This is a familiar pattern in physics. A theory works well, then tiny cracks appear at the edges, and those cracks turn out to be windows. They show where the old theory is not wrong exactly, but incomplete. Newton's gravity remains an excellent approximation when gravity is weak and speeds are slow compared with light. Einstein did not throw Newton away. He placed Newton inside a broader structure. One of the most surprising consequences of general relativity is that gravity affects time. A clock deeper in a gravitational field ticks more slowly compared with a clock higher up, away from the mass. This is not because the clock is damaged or sleepy or in need of a better morning routine. Time itself is involved in the geometry. Near massive objects, the relationship between time and space changes. On Earth, the effect is small, but it can be measured. It also matters for satellite navigation. Satellites orbit high above Earth, where gravity is weaker, and they are also moving quickly. Both gravity and motion affect their clocks. If these effects were ignored, navigation systems would become inaccurate. So whenever a phone helps guide someone through city streets, general relativity is quietly included in the calculation, like a Nobel Prize-winning assistant hidden inside the map app. The theory also predicts gravitational waves. If massive objects accelerate in certain ways, they can create ripples in space-time that travel outward at the speed of light. These are not waves moving through space-time like sound through air. They're waves of space-time geometry itself. For decades, gravitational waves were a prediction waiting for direct detection. The effects are extremely small by the time such waves reach Earth. A passing wave from a distant black hole collision changes lengths by an amount far beyond ordinary perception. Yet with extraordinarily sensitive instruments, scientists finally detected these ripples. The signals matched the predictions of general relativity and opened a new branch of astronomy. We can now observe the universe not only through light, but through the motion of space-time itself. Black holes are another major consequence of Einstein's gravity. If enough mass is compressed into a small enough region, space-time curves so strongly that an event horizon forms. Inside that boundary, escape outward becomes impossible. Light cannot get out, not because it is too weak in the usual sense, but because the paths that would lead outward no longer lead outward in the required way. This is a hard idea because our everyday minds expect space to behave like a room, where directions remain available if only we move fast enough. Near a black hole, the structure of space-time itself changes the meaning of possible paths. General relativity describes this with great power, but black holes also point toward the need for quantum gravity. They are places where gravity is extreme, space-time is deeply curved, and quantum effects cannot be ignored forever. This brings us closer to the graviton. In Newton's view, gravity is a force between masses. In Einstein's view, gravity is curved space-time. The graviton idea seems at first to return gravity to the language of force-carrying particles. That can feel like a step backward, as if we are undoing Einstein and going back to invisible pulls. But that's not quite right. A quantum theory of gravity would need to reproduce general relativity in the situations where general relativity works. The graviton, in the usual view, would be a tiny quantum ripple of the gravitational field. In calm, weak gravity, those ripples can be described in a way somewhat similar to other force carriers. But the full theory must still explain curved space-time. It cannot simply ignore Einstein. It must show how Einstein's smooth geometry emerges from quantum behaviour. This is one reason the graviton is harder to understand than the photon. The photon is the quantum of the electromagnetic field, and electromagnetic fields exist within space-time. We can describe light travelling through space-time interacting with charged particles. But gravity is different because in general relativity the gravitational field is space-time geometry. Trying to quantize gravity may mean trying to quantize the thing that defines distances and durations in the first place. The graviton would not just be a particle moving on the stage, it would be connected to tiny disturbances of the stage itself. And if the stage can fluctuate, then our usual ideas of where and when become less firm at the deeper scales. The path from Newton to Einstein is therefore not just a historical upgrade. It changes the question that the graviton must answer. If gravity were only a force pulling masses together, one might simply ask what particle carries that force. But after Einstein, the question becomes more subtle. What does it mean for space-time geometry to have quantum excitations? Can the smooth curvature of general relativity be made from countless quantum pieces? Is the graviton one of those pieces, or only an approximate way of speaking when gravity is weak and space-time is nearly flat? These questions remain open because we do not yet have a complete tested theory of quantum gravity. Still, Newton's picture remains valuable. It teaches us gravity's universality, and its power to connect the fall of a small object with the motion of worlds. Einstein's picture teaches us that gravity is not merely an invisible attraction, but a feature of space-time itself. Both are needed for the story. Newton gives us the first great unification of earth and sky. Einstein gives us the deeper view that motion, time, light, and geometry are bound together. The graviton waits beyond them, not as a rejection of either, but as a sign that the story may have another layer. It is worth pausing on how strange this progression is. We began with objects falling downward. Then we learned that falling and orbiting are related. Then we learned that gravity is not simply a pull but the curvature of spacetime. Then we found that time itself changes in gravity. Light bends, black holes form, and spacetime can ripple across the universe. All of that grows from asking why things fall. It is a reminder that ordinary questions are not always small. A falling apple, if followed carefully enough, leads to the structure of the cosmos. In a quiet room, gravity may not seem dramatic. It is just the reason the blanket rests on you and the floor remains where you expect it. But beneath that ordinary steadiness is a history of changing ideas. Newton saw a universal attraction reaching across space. Einstein saw geometry guiding motion. Modern physicists see a further problem waiting at the border with quantum theory. Each view brings gravity into sharper focus, but none makes it entirely simple. The invisible hand has become an invisible curvature, and perhaps at the smallest level it may become a field with quantum ripples. To approach that next step, we have to leave the smooth paths of planets for the restless world of particles, where forces are described through fields, interactions, and tiny messengers that behave nothing like the solid little objects our imagination first tries to place in their role. To move from Einstein's curved spacetime into the idea of a graviton, we have to step into a very different kind of physics. Not the grand sweeping physics of planets and stars, where motion can be drawn as smooth curves, and time feels steady enough to organise a train schedule. This next world is smaller, stranger, and much less willing to behave like the objects on your kitchen table. It is the quantum world, the world of atoms, particles, fields, probabilities, and tiny messengers. It is also the world that makes your table solid, your lamp glow, your phone work, and your body possible. So although it may sound remote, it is not far away at all. It is underneath everything, quietly running the machinery while ordinary life carries on above it. Rather like a very serious backstage crew during a calm bedtime program. At first glance, the quantum world seems to be about particles, electrons, photons, quarks, neutrinos, and other small things with names that sound as if someone shook a box of alphabet tiles during a physics conference. But modern physics does not really treat these particles as tiny balls flying through space. That picture is useful for beginners, and occasionally useful for experts when they're trying to explain something before the kettle boils, but it is not the deeper view. The deeper view is that the universe is filled with fields. A field is something that has a value or condition at every place in space and time. The electromagnetic field is one example. The electron field is another. The quark fields are others. These fields are not made of ordinary material in the way a blanket is made of thread. They are basic ingredients in our best description of nature. A particle, in this view, is a little disturbance or excitation of a field. If the field is calm, there may be no particle present. If the field is excited in a particular way, we call that excitation a particle. This is often compared to a ripple on water, and although the comparison is not perfect, it helps. A ripple is not separate from the water. It is the water moving in a particular pattern. A photon is not a tiny bead of light in the everyday sense. It is a quantum excitation of the electromagnetic field. An electron is an excitation of the electron field. The particle is the field showing up in a countable way. This is already a bit odd, because our senses are used to objects being separate from their surroundings. A cup is not usually described as an excited patch of cup field, though after enough coffee one might be willing to consider it. Quantum physics became necessary because the older smooth descriptions of nature could not explain what experiments were showing. Light, for example, behaves like a wave in some situations. It spreads out, interferes with itself, and creates patterns that look very wave-like. But light also arrives in packets. It can be absorbed and emitted in discrete amounts. Matter behaves strangely too. Electrons can act like particles in one experiment and like waves in another. This is not because electrons are confused or because they are trying to be mysterious for attention. It is because our everyday categories, particle and wave, come from large-scale experience. Quantum objects do not fit neatly into either category. They are described by a mathematical structure that gives probabilities for what we might observe. This probabilistic nature is one of the main reasons quantum physics feels so unsettling. In ordinary life, if a ball is rolling across the floor, we expect it to have a definite position and speed, even if we are not looking. In quantum physics, certain properties are not simply waiting with definite values in the same familiar way. Before measurement, the theory gives us a range of possible outcomes and the chances of each. When we observe the system, we get one result. The theory is extremely accurate in predicting the patterns of many results, but it does not behave like a hidden clockwork mechanism in the old sense. It is not that we merely lack information in the same way we might not know which drawer contains the biscuits. The structure of nature itself appears to involve uncertainty. This does not mean anything can happen. Quantum physics is not a permission slip for nonsense. It has rules, and they are strict. They're just not the rules our intuition would have guessed. Particles do not wander around doing whatever they like. Their behavior follows precise patterns, and those patterns have been tested with extraordinary accuracy. The reason the quantum world seems strange is not that it is vague. It is strange because it is exact in a way that does not match ordinary mental pictures. Nature, at its smallest scales, is not blurry because scientists are sleepy. It is governed by rules where probability is built in. The idea of tiny messengers comes from quantum field theory, which is the framework used to describe particles and forces together. In this view, forces arise through interactions between fields, and those interactions can often be described in terms of exchange particles. These are sometimes called force carriers or messenger particles. The word messenger is friendly, but it should not be taken too literally. A photon does not put on a little hat and carry a note from one electron to another saying, "Please repel at your earliest convenience." Still, the image gives a useful starting point. When charged particles interact electromagnetically, the photon is the quantum associated with that interaction. It is the messenger of the electromagnetic force. Electromagnetism is a good example because it is familiar and powerful. It is responsible for light, electricity, magnetism, radio waves, chemistry, and the structure of atoms and molecules. When two electrons repel each other, that repulsion is electromagnetic. When an electron is bound to an atomic nucleus, that attraction is electromagnetic. When a lamp shines, photons are emitted. When your eyes detect that light, photons are absorbed by molecules in your retina, starting a chain of biological events that eventually becomes vision. The same field that lets a magnet stick to a refrigerator also carries sunlight across space. Electromagnetism is not a minor feature of the world. It is one of the main reasons the world has texture, colour, chemistry, and functioning toasters. The photon is massless, so electromagnetic influence can reach across very long distances, but the electromagnetic force can also cancel out because electric charge comes in positive and negative forms. Large objects are usually almost neutral overall, with positive and negative charges balanced. That is why you do not feel the electromagnetic pull of distant stars in the same direct way you feel Earth's gravity. On smaller scales, though, electromagnetism is enormously stronger than gravity. A tiny magnet can lift a paperclip against the pull of the whole Earth. That simple demonstration is one of the most charming insults ever delivered to gravity. The entire planet pulls downward, and a little magnet on a desk says, "No thank you, I have this." The strong nuclear force is another fundamental interaction, and it has its own messenger particles called gluons. The strong force binds quarks together inside protons and neutrons, and it is also connected to the force that holds atomic nuclei together. Without it, atoms as we know them would not exist. Protons are positively charged, so electromagnetism makes them repel one another. In the nucleus, the strong force overcomes that repulsion at very short distances, allowing nuclei to hold together. It is a force of tremendous strength, but it does not reach far beyond the scale of atomic nuclei. It is like a very powerful person who refuses to leave the room. Extremely important, very intense, but not useful for pulling planets around stars. Gluons are different from photons in an important way. Photons carry electromagnetic influence, but do not themselves carry electric charge. Gluons, however, participate strongly in the force they carry. They interact with one another in a rich and complicated way. This helps make the strong force behave very differently from electromagnetism. Quarks are never found alone in ordinary conditions. They are confined inside composite particles. If you try to separate them, the energy involved does not simply free one quark in the way you might pull apart two magnets. Instead, the field responds in a way that creates more particles. The strong force is not only strong, it is deeply self-involved, which in human company would be difficult, but in nuclear physics is essential. The weak nuclear force has its own messenger particles as well. These are heavy compared with photons and gluons, and because they are heavy, the weak force acts only over very short distances. The weak force is responsible for certain kinds of radioactive decay and plays a crucial role in processes inside stars, including reactions connected to how the sun shines. It also interacts with neutrinos, those nearly ghost-like particles that pass through matter with remarkable ease. Every second, enormous numbers of neutrinos from the sun pass through your body. Nearly all of them continue through the Earth as if the planet were a light fog. This is not something to worry about. If they were more sociable particles, we would have noticed by now. Together, electromagnetism, the strong force, and the weak force are described by a quantum framework that has been tested in great detail. This framework is often called the standard model of particle physics. It is not a model in the sense of a plastic airplane on a shelf. It is a deep theoretical structure that organizes known particles and their interactions. It includes matter particles such as quarks and electrons, and force-carrying particles such as photons and gluons. It also includes the Higgs field, whose excitation is the Higgs boson, a particle discovered after decades of searching. The Higgs field helps explain why many particles have mass. The discovery of the Higgs boson was a major confirmation that the field was not just an elegant idea, but part of physical reality. The standard model is one of the most successful scientific theories ever made, but it does not include gravity in the same way. That omission is not small. Gravity is one of the fundamental features of the universe. It shapes the cosmos, governs planets, and creates black holes. Yet in particle physics, gravity remains outside the main quantum framework. This does not mean particle physicists forgot gravity somewhere behind the laboratory sofa. They know very well it is there. The difficulty is that gravity behaves differently from the other forces, and attempts to treat it with the same ordinary quantum methods run into deep problems. To understand why the graviton seems natural at first, it helps to return to the messenger idea. If electromagnetism has photons, the strong force has gluons, and the weak force has its heavy messengers, then perhaps gravity has a messenger too. That hypothetical messenger is the graviton. In a simple weak field picture, where space-time is almost flat and gravity is treated as a small disturbance, a graviton can be described as the quantum of that disturbance. It would be the smallest packet of gravitational radiation, much as a photon is the smallest packet of electromagnetic radiation. If a gravitational wave is a ripple in space-time, then a quantum version of that ripple would involve gravitons. But the phrase simple weak field picture is doing a lot of work. It is the kind of phrase that looks calm while quietly carrying a piano upstairs. Gravity is not just another field placed on top of space-time. In Einstein's theory, gravity is tied to spacetime itself. The gravitational field is the geometry that defines distances, durations, and motion. When we try to describe gravitons, we're trying to treat tiny ripples of geometry in a quantum way. That is much more subtle than quantizing a field that lives inside a fixed background. With the photon, spacetime is the arena in which the electromagnetic field behaves. With the graviton, the arena itself may be fluctuating. It is like trying to describe waves on a pond while the measuring ruler, the clock, and the idea of where the pond is are all part of the water. In ordinary quantum field theory, interactions are often pictured through diagrams where particles exchange messenger particles. These diagrams are calculation tools, not literal photographs. They help physicists organize possibilities and predict results. Some messenger particles in such diagrams are called virtual particles. This phrase can cause confusion. Virtual particles are not little objects briefly popping into existence in exactly the same way as particles that can be directly detected. They are features of the calculation, representing possible intermediate effects. They are useful and meaningful within the mathematics, but they should not be imagined as tiny sparks constantly appearing and disappearing, like microscopic fireflies having a busy evening. The real quantum world is strange enough without adding extra cartoons too confidently. Still, the exchange picture gives an intuitive bridge. If two electrons repel each other, the interaction can be described through photon exchange. If two masses attract gravitationally in a quantum approximation, the interaction might be described through graviton exchange. In that sense, gravitons would help explain how gravity appears as a force between particles in a quantum setting. But the deeper theory would still have to match general relativity when many gravitons act together, or when gravity becomes smooth on large scales. A classical gravitational field, like Earth's gravity, would correspond not to one graviton, but to an enormous collective state, just as a bright beam of light contains many photons. We do not experience individual photons in sunlight as separate taps on the skin. We experience the combined effect as warmth and brightness. Likewise, if gravity is quantum, we experience not individual gravitons, but the smooth averaged behaviour of vast numbers, or a classical field emerging from the underlying quantum description. The trouble is that individual gravitons would interact incredibly weakly. Gravity is feeble at particle scales. A single graviton passing through a detector would almost never leave a trace. To catch one, a detector would need to be unbelievably sensitive, and even then the universe would not make it easy. Noise from other particles, vibrations, thermal effects, and ordinary gravity from nearby objects would overwhelm the signal. Some arguments suggest that a detector capable of reliably measuring a single graviton would need to be so extreme that it would create its own gravitational collapse. That is the sort of experimental challenge that makes even very patient scientists stare quietly into their tea. This weakness is also why quantum gravity is hard to test directly. The energies at which gravity becomes strongly quantum are far beyond what our particle accelerators can reach. In everyday particle experiments, gravity is so tiny compared with the other forces that it can be ignored. That is not because gravity is unimportant, but because it is irrelevant at those scales in practice. A proton in a collider is influenced overwhelmingly by the strong, weak, and electromagnetic interactions. Its gravitational pull on another proton is absurdly small. Asking a particle collider to reveal quantum gravity directly is a little like asking a whisper to dominate a brass band during a parade. The whisper exists, but good luck making it the loudest sound in the street. Even so, the quantum world keeps pointing toward gravity in indirect ways. Black holes, for example, combine gravity, quantum effects, and thermodynamics. The early universe was once extremely dense and hot, a setting where quantum gravity may have been important. Gravitational waves from cosmic events might carry clues about the nature of space-time, even if they do not let us count individual gravitons. Precision experiments may one day reveal tiny deviations from known physics. The search is not hopeless, It is just difficult in a way that requires cleverness rather than brute force alone. Nature has locked the door, but physicists are very good at checking windows, chimneys, and suspiciously loose floorboards. The messenger particle idea also teaches us something more general. Forces are not separate magical commands imposed on matter. They arise from fields and interactions. The universe is not made of isolated objects bumping through emptiness while forces somehow tug from nowhere. It is made of fields that fill space-time, and what we call particles are excitations of those fields. Matter particles and force carriers are woven into one framework. Interactions happen because fields couple to one another. This view is more unified than the everyday picture, but also less visual. There are no tiny strings, hooks, or hands. There are patterns, probabilities, exchanges, and measurable outcomes. When we apply this thinking to gravity, we begin to see why the graviton is both appealing and troubling. It is appealing because it fits the quantum habit. If fields have quanta, and if gravity has waves, then gravitons seem like the natural quanta of gravitational waves. It is troubling because gravity is not merely a field in space-time in the ordinary sense. It is related to space-time itself. The graviton may therefore be only part of the answer, valid when gravity is weak and the background is nearly calm. In stronger situations, such as near black holes or at the beginning of the universe, the particle picture may not be enough. Something deeper may be needed. This is not unusual in physics. Different descriptions can be valid in different regimes. Water can be described as a smooth fluid when you're studying waves in a bathtub, but at a deeper level it is made of molecules. You do not need to track every molecule to understand a bathtub wave. In the same way, space-time may look smooth at large scales while having a quantum structure underneath. The graviton could be like the small ripple description of that structure, useful in certain situations but not the full story. Or it could be a necessary ingredient in a complete theory still waiting to be discovered. We do not yet know which picture will win, and the universe has not provided an answer key, which seems inconsiderate but traditional. For now, the quantum world gives us a language. Fields fill reality. Particles are excitations. Forces can be described through messenger particles. Photons carry electromagnetic influence. Gluons belong to the strong force. The weak force has heavy carriers. The Higgs boson reflects the Higgs field, and somewhere beyond the confirmed list, the graviton waits as the proposed quantum of gravity. It is not confirmed, not detected, and not yet placed into a complete theory that unites everything. But it is not an arbitrary guess. It is the shape of an expectation created by the success of quantum field theory and the existence of gravitational waves. As the room grows quieter and the idea settles, the graviton begins to look less like a tiny missing marble and more like a question with a particle-shaped outline. It asks whether gravity can be made quantum in the same way as the other forces. It asks whether space-time itself has small excitations. It asks how the smooth bending of Einstein's universe could arise from the restless behaviour of fields. And it asks why the most familiar force in our lives is the hardest one to hear at the smallest scales. The next step is to look directly at what this proposed particle would actually be, not as a simple speck flying through space, but as a very specific kind of quantum ripple with properties shaped by everything gravity must do, from making objects fall to carrying waves across the universe. Now that the quantum world has given us its way of speaking, we can turn toward the graviton itself and ask the question plainly. What would it actually be? Not what would it look like under a microscope, because that image would lead us down the wrong path almost immediately. No one expects a graviton to be a tiny bead, a grain of cosmic dust, or a little silver pellet of gravity drifting through space with a serious expression. If gravitons exist, they would belong to the same strange family as photons and gluons. They would be quanta of a field. They would be the smallest possible disturbances associated with gravity, the way a photon is the smallest possible disturbance associated with light and electromagnetism. The difficulty is that gravity is not just another force placed neatly beside the others. Gravity is tied to space-time itself. and that makes the graviton a very unusual guest at the particle table. A useful way to begin is with gravitational waves. We know gravitational waves exist because detectors on Earth have measured them. When massive objects such as black holes or neutron stars spiral together and merge, they disturb spacetime. Those disturbances travel outward across the universe at the speed of light. By the time they reach us, they are incredibly weak, but sensitive instruments can detect the tiny stretching and squeezing they produce. In Einstein's theory, a gravitational wave is a smooth ripple in spacetime. It is not a ripple moving through air, water, or some hidden substance. It is a ripple of the geometry of space and time themselves. Distances change very slightly as the wave passes. The shape of space-time trembles. Now imagine trying to describe that same ripple using quantum theory. In quantum physics, waves often come in packets. Light can behave as a smooth electromagnetic wave, but when it is emitted or absorbed, it comes in discrete quanta called photons. A bright beam of light contains many photons. A faint source may release them one by one. In a similar way, if gravitational waves are quantum at the deepest level, then a gravitational wave would be made of many gravitons. A single graviton would be the smallest quantum of gravitational radiation. It would be the most delicate possible ripple of gravity, far too small and weak to notice in daily life, and perhaps far too difficult to detect even with any experiment we can realistically build. That is the first important idea. A graviton would not be gravity itself in the whole familiar sense. It would not be the reason you feel weight as a single little particle pulling you downward. The gravity you experience from Earth would be a large-scale, classical effect. If gravity is quantum underneath, the field associated with Earth's gravity would involve an enormous collective situation, not one lonely graviton tugging at your shoes. It would be more like the difference between an ocean wave and a single molecule of water, though even that comparison is imperfect. You can float on the ocean without thinking about individual molecules. You can feel Earth's gravity without interacting with individual gravitons in any practical noticeable way. In the usual theoretical picture, a graviton would be massless. That matters because gravity reaches across unlimited distances. Forces that extend over long ranges are associated with massless carrier particles. The photon is massless, and electromagnetic waves can travel across the universe. If the graviton had ordinary mass, gravity would behave differently over very large distances. It would fade in a way that does not match what we observe. So the simplest and most accepted expectation is that the graviton has no rest mass and travels at the speed of light. This agrees with what we know from gravitational waves, which move at the same speed as light to extremely high accuracy. A graviton would also have a property called spin. This is not spin in the ordinary sense of a tiny ball rotating like a planet. Quantum spin is a built-in kind of angular momentum, a property that shapes how a particle behaves and how it interacts. Photons have spin 1. Gravitons, in the standard picture, would have spin 2. That detail is not decorative. It is deeply connected to the kind of force gravity is. A spin 2 massless particle naturally leads to an attractive interaction that couples to energy and momentum, and with the right structure, it points toward the equations of general relativity. In plain language, the expected spin of the graviton is one reason it fits gravity, rather than some other force. The graviton is not just any hypothetical particle with a dramatic name. Its properties are tightly constrained by what gravity must do. The spin 2 nature also helps explain why gravity is universal. Gravity does not only respond to electric charge, as electromagnetism does. It responds to energy, mass, pressure, motion, and the overall contents that shape spacetime. Everything with energy participates. Light is affected by gravity. Matter is affected by gravity. Even gravity itself carries energy and can influence gravity. This universality is one reason gravity cannot be screened in the ordinary way. You can block light with a curtain. You can shield certain electric fields with conducting materials, but there is no ordinary gravity curtain. If there were, home renovation would become very interesting and probably very unsafe. The graviton, if it exists, would carry the quantum version of this universal coupling. But here is where the simple messenger picture begins to wobble. With electromagnetism, we can say that photons carry electromagnetic interactions between charged particles. That is already a simplified picture, but it is manageable because the electromagnetic field lives in space-time. The photon moves through space-time. Gravity is different. In general relativity, gravity is not merely a field inside space-time, it is the curvature of space-time. So when we talk about gravitons, we're talking about quantum excitations of the very structure that defines distance and duration. A photon is like a ripple in something that lives on the stage. A graviton is more like a ripple in the stage itself. And if the stage itself can ripple, then our usual idea of a fixed background becomes less reliable. This is one of the reasons the graviton is usually introduced in a limited setting. Physicists often begin by imagining space-time as almost flat, with gravity as a tiny disturbance on top of it. In that weak gravity situation, the mathematics can be treated in a way that resembles other quantum fields. The small disturbance can be quantized, and the quanta are gravitons. This approach works as an approximation. It lets physicists calculate how gravitons might behave when gravity is weak and space-time is not too curved. That is useful, but it is not the full theory of quantum gravity. It is like learning about small ripples on a calm pond while postponing the question of what happens during a storm when the pond, the shore, and the measuring stick are all being shaken at once. A single graviton would carry an incredibly tiny amount of energy. The exact amount would depend on the frequency of the gravitational wave it belongs to, just as the energy of a photon depends on the frequency of light. But gravitational waves we can detect from cosmic events are made of vast numbers of extremely low-energy gravitons if we describe them in that language. The combined wave can be measured, but the individual quanta are far beyond reach. It is similar to hearing a distant rumble and trying to separate one single vibration from it, except the vibration interacts so weakly that it almost never leaves a trace. A graviton could pass through a detector, a planet, or a star with almost no chance of being absorbed. This weak interaction is not a small technical inconvenience. It is central to why the graviton remains hypothetical. The photon interacts readily with charged particles. That is why cameras work, eyes work, solar panels work, and why a flashlight is not a philosophical proposal. Neutrinos interact much more weakly, and detecting them already requires enormous detectors and patience. Gravitons would interact far more weakly still. They're not merely shy, they are practically professional at avoiding detection. To catch one directly, you would need a detector of such extraordinary sensitivity and size that other physical limits may make the task impossible. Some arguments suggest that a detector capable of measuring a single graviton would have to be so massive or so precise that it would collapse into a black hole before doing the job. That is one of those moments when nature seems to say, in a very calm voice, perhaps try another method. So if we may never detect a single graviton directly, why do physicists take the idea seriously? Because science is not only a list of things already seen, it is also a structure of explanations. The graviton arises naturally when we apply quantum reasoning to weak gravitational waves. It is required by many approaches that treat gravity as a quantum field at low energies. It is consistent with the idea that classical waves are built from quantum excitations, and it helps connect gravity with the broader language of particle physics. The graviton is not confirmed, but it is not a random guess. It is the expected particle-shaped shadow of quantum gravity in situations where gravity is gentle enough to be treated like other fields. There is an important distinction here. The existence of a graviton in the low-energy approximation does not automatically mean we understand quantum gravity completely. It would be possible for gravitons to appear as useful low-energy excitations, while the deeper structure of space-time is very different. Sound waves in a solid can be described in terms of quanta called phonons, but phonons are not fundamental particles in the same sense as electrons. They are collective excitations of atoms in a material. Some physicists wonder whether gravitons might be similar in spirit, not fundamental building blocks of the universe, but emergent excitations of a deeper quantum structure. If spacetime itself emerges from something more basic, then the graviton could be a ripple of that emergent spacetime, rather than the final ingredient at the bottom of reality. This does not make the graviton less important. Emergent things can be very real. A wave is real even if it is made of water molecules. Sound is real even if it emerges from atoms moving together. Temperature is real even though one lonely molecule does not have temperature in the everyday thermodynamic sense. If gravitons are emergent, they could still describe real quantum gravitational waves in the correct setting. The question is whether they are fundamental or whether they are the low-energy language of something deeper. That question is still open. Another property of the graviton is that it would be its own antiparticle. Some particles have distinct antiparticles. The electron has the positron, but the photon is its own antiparticle, and the graviton is expected to be the same. This means there would not be a separate antigraviton with opposite gravitational charge in the ordinary sense. Gravity does not have positive and negative mass charges that cancel like electric charges. The universal attraction of gravity is part of why large-scale structure forms so effectively. If there were ordinary negative gravitational charge in the same way there is negative electric charge, the universe would be a very different place, and possibly one with much more complicated furniture assembly. The graviton would also interact with other gravitons. This follows from the fact that gravity itself carries energy, and energy gravitates. In electromagnetism, photons do not directly interact with one another in the simplest classical picture, because they do not carry electric charge. Gluons do interact with one another because they carry the kind of charge associated with the strong force. Gravity has its own version of self-interaction, because gravitational fields contain energy, and that energy contributes to gravity. This self-interaction is one of the reasons the full quantum theory becomes difficult. The graviton is not simply a quiet messenger passing notes between particles. It is part of a field that can affect itself, curve its own background, and become deeply non-linear when gravity is strong. In ordinary words, gravity does not only speak to matter, it also listens to itself and then responds. If you imagine many gravitons together, you might get something resembling a classical gravitational wave. If you imagine a vast coherent state of gravitons associated with a planet or star, you might recover the smooth gravitational field of everyday and astronomical physics. This idea is similar to how many photons can make a classical light wave. A radio wave, a laser beam, or sunlight can often be described as electromagnetic waves without tracking individual photons. The quantum description is still underneath, but the large-scale behavior is smooth. The same may be true for gravity, at least in weak situations. The smooth curvature of space-time may be the collective behavior of something quantum, but caution is needed. Curved space-time is not just a force field in the old sense. If gravitons are quanta of space-time curvature, then asking where a graviton is can become tricky. In ordinary quantum field theory, we describe particles against a background of space and time. We say a particle is here or there, earlier or later, with quantum uncertainty. But if the particle is part of the quantum structure of space-time itself, the background is not fixed in the same way. At the deepest level, the ideas of here and there may depend on the gravitational field. This is why quantum gravity is not simply a matter of adding one missing particle to the standard model and then going home early. The graviton is a doorway, not the whole house. It is also worth noting what a graviton would not do. It would not explain gravity by replacing Einstein with a tiny mechanical pull in the old-fashioned sense. A proper quantum theory must reproduce general relativity at large scales. If gravitons exist, they must collectively give rise to curved space-time. They must not undo the bending of light, the slowing of clocks in gravity, the existence of black holes, or the detection of gravitational waves. Any theory that says, never mind Einstein, gravity is just little pellets pulling things together, would fail immediately. The graviton must be compatible with the geometric nature of gravity. That is what makes it interesting and difficult. A graviton would also not be part of the confirmed standard model. The standard model describes known particles and 3 of the fundamental interactions in quantum terms, but it does not include a working quantum theory of gravity. Sometimes people casually place the graviton beside the photon, gluon, and weak force carriers as if it is simply the missing member of the band. In a loose educational sense, that is understandable, but scientifically the graviton remains hypothetical because the full quantum gravity framework is not established experimentally. The band has an empty chair, yes, but we're not entirely sure whether the missing musician plays a violin, a drum, or an instrument made of space-time that has not been invented yet. The graviton also raises the question of scale. Quantum gravity is expected to become crucial at incredibly tiny distances and incredibly high energies, far beyond ordinary experiments. At those scales, space-time might not remain smooth. It could fluctuate strongly. It could have a discrete structure. It could be described by strings, loops, networks, information, or something else entirely. In such regimes, the simple graviton picture may break down. Just as sound waves make sense in air at ordinary scales but not as a description of individual molecules alone, gravitons may make sense only when spacetime is already smooth enough for ripples to be defined. This is why different approaches to quantum gravity treat the graviton in different ways. In string theory, a graviton appears naturally as one of the vibration modes of a string. That was one of the reasons string theory became so compelling to many physicists. A theory originally explored for other reasons unexpectedly contained a massless spin 2 particle, exactly the kind associated with gravity. In loop quantum gravity, the focus is different, with space-time geometry itself quantized in a non-particle-based way, though one still expects ordinary gravitons to emerge in suitable low-energy limits if the theory is to match known physics. Other approaches explore gravity as emergent from quantum entanglement or information. Across these views, the graviton may be fundamental, emergent, approximate, or a clue pointing towards something deeper. For a calm mental picture, imagine a very large lake at dawn. From far away, the surface looks smooth, then a breeze crosses it and waves move gently across. If you were studying the lake only at the scale of those waves, you could describe their speed, shape, and direction without knowing every molecule of water. If you zoomed far enough in, the smooth surface would disappear into molecular motion. The wave would still be real, but it would no longer be the most basic thing. Spacetime may be something like that, though the comparison should be handled gently. General relativity describes the smooth lake. Gravitational waves are ripples on it. The graviton would be the smallest quantum ripple in the weak calm limit, but what the lake is made of, if it is made of anything more basic at all, remains unknown. This uncertainty is not a failure. It is the honest frontier. Physics is full of ideas that were first understood as useful approximations and later placed into deeper frameworks. Newton's gravity was not thrown away by Einstein. It became the low-speed, weak gravity limit of general relativity. Classical electromagnetism was not discarded by quantum theory. It became the large-scale behaviour of quantum electrodynamics. In the same way, the graviton may eventually become part of a broader theory that explains when and why the particle description works. Or it may be replaced by language we cannot yet fully imagine. Either way, asking what the graviton would be is a way of testing how far our current ideas can reach. In practical terms, if someone asks what a graviton is, the best careful answer is this. A graviton is the hypothetical quantum particle associated with gravity, especially with gravitational waves in a weak field quantum description. It is expected to be massless, to travel at the speed of light, to have spin too, and to interact with all forms of energy and momentum. It has never been directly detected, and it is not part of an experimentally confirmed theory of quantum gravity. It is a theoretical prediction that appears when physicists try to bring gravity into the quantum framework. That answer is precise, but it can sound a little dry, like reading the label on a jar when the jar contains a storm. The deeper meaning is that the graviton is where our two great languages of nature meet uneasily. One language says gravity is the curvature of spacetime. The other says fields have quantum excitations and interactions occur in discrete ways. The graviton is what appears when we ask whether curved spacetime can have a smallest ripple. It is gravity translated into the grammar of quanta. Whether that translation is complete or only approximate is the great question. So a graviton would be tiny in influence, but enormous in meaning. It would connect the fall of an apple to the quantum behavior of fields. It would link gravitational waves from black hole mergers to the particle language used for light and matter. It would suggest that even space-time, the arena of all events, has a quantum side. Yet it remains hidden, because gravity is so weak at small scales, and because the most direct signs of quantum gravity are far beyond ordinary reach. The missing particle of gravity is not missing because no one has looked. It is missing because the universe has made it almost perfectly quiet. And that quietness leads naturally to the next problem, because once we understand what a graviton would be, the next question is why catching one may be among the hardest tasks physics could ever attempt. By now, the graviton has begun to take shape as an idea, not as a tiny marble of gravity, but as the smallest possible quantum ripple of the gravitational field. It is what we would expect if gravity, like light, has a particle side. A beam of light can be described as many photons acting together. A gravitational wave in the same kind of thinking could be described as many gravitons acting together. That sounds neat and almost reassuring, as if the universe has simply left one particle off the list and physicists only need to look under the cosmic sofa cushions. But this is where the story becomes less like a tidy missing object, and more like a problem designed by nature after a very long evening of making things difficult. The graviton is not merely hard to detect, merely hard. It may be so difficult to detect directly that no realistic experiment can ever catch one in isolation. Not because physicists lack imagination, and not because the instruments are poorly made, but because gravity itself is almost unbelievably weak at the scale of single particles. That can feel wrong at first. Gravity does not seem weak when you are climbing stairs, carrying luggage, or trying to get out of bed before sunrise. It certainly does not feel weak when a dropped mug hits the floor with a sound that suggests both tragedy and cleaning. Gravity feels firm. It feels constant. It feels like the most unavoidable force in ordinary life. But the gravity you feel is not the gravity of one particle acting on another. It is the combined pull of the entire Earth. Every mountain, ocean, layer of rock, and deep metallic region beneath your feet contributes. You are not being held down by a small local effect. You are being pulled by a whole planet. And even then, a simple refrigerator magnet can lift a paperclip against that planetary pull. A small magnet, barely trying, defeats the gravity of Earth for that little piece of metal. It is a wonderfully rude demonstration of just how weak gravity is compared with electromagnetism. On the scale of atoms and particles, gravity is so faint that it almost disappears beneath the louder forces. Electromagnetism shapes atoms, chemistry, light, electricity, and the structure of materials. The strong nuclear force binds quarks and atomic nuclei. The weak nuclear force changes particles in radioactive processes and helps stars shine. Gravity is present, but in particle physics experiments it is usually so small that it can be ignored entirely. That is not because gravity is absent. It is because its influence is buried under effects that are enormously stronger. If the other forces are people speaking across a room, gravity is someone breathing quietly in the next building while a marching band goes by. The breath is real. Good luck measuring it. This weakness is the first major reason finding a graviton is so hard. To detect a particle, it must interact with your detector in some way. A photon interacts readily with charged particles. That is why your eyes can detect light, cameras can capture images, and solar panels can turn sunlight into electricity. Neutrinos interact much less readily, which is why detecting them requires large tanks, deep underground laboratories, or enormous volumes of ice instrumented with sensitive sensors. Even neutrinos, famous for passing through planets, almost as if nothing is there, occasionally interact often enough that we can build experiments to study them. Gravitons would be far more elusive. A single graviton could pass through ordinary matter, through a laboratory, through the whole Earth, with almost no chance of leaving any trace at all. This is not only a matter of making a bigger detector. Bigger often helps in particle physics, but with gravitons the problem becomes almost absurd. The interaction is so weak that to have a reasonable chance of catching one, a detector would need to contain an enormous amount of matter, operate with extraordinary precision, and be shielded from almost every other disturbance. But as the detector becomes more massive, it creates its own gravity. As it becomes more sensitive, it becomes more vulnerable to noise. As it becomes larger, it becomes harder to isolate. At some point, proposals run into physical limits. There are arguments that a detector massive enough and sensitive enough to detect a single graviton directly might collapse into a black hole before succeeding. That is not a minor engineering inconvenience. That is the universe taking the detector away and replacing it with a horizon. Even if a detector did not collapse, the signal from one graviton would be unbelievably small. Think about what detection usually means. A particle arrives, transfers energy, changes the state of an atom, produces a flash of light, creates an electrical signal, or leaves some measurable mark. The mark must be strong enough to rise above noise. Noise is everywhere. Thermal vibrations shake atoms. Electromagnetic fields interfere. Cosmic rays pass through. Radioactivity produces stray events. Nearby traffic, distant earthquakes, ocean waves, and even tiny temperature changes can affect sensitive instruments. A graviton would deposit so little energy and interact so rarely that its signal would be drowned in a sea of ordinary physical activity. It would be like trying to hear one particular grain of sugar land on a carpet during a thunderstorm while someone in the next room is rearranging furniture. The gravitational wave detectors that have already succeeded are among the most sensitive instruments ever built. They can measure tiny changes in distance caused by passing gravitational waves from events such as black hole mergers. These instruments use long arms, laser light, mirrors, and careful isolation to detect the stretching and squeezing of space-time. Their achievement is extraordinary. But they do not detect individual gravitons. They detect classical gravitational waves, the collective effect of enormous numbers of possible gravitational quanta acting together. This distinction matters. Detecting an ocean wave is not the same as counting one molecule of water in it. Hearing a symphony is not the same as measuring the motion of one air molecule caused by one violin string. Gravitational wave astronomy has shown us that space-time can ripple, but the waves are large-scale signals. The individual quantum grains, if that is the right word, remain hidden far below the level of direct measurement. A helpful comparison is light. In bright sunlight, photons are so numerous that light behaves almost like a continuous wave. Your eyes do not notice every photon separately in ordinary conditions, but with sufficiently sensitive equipment, single photons can be detected. This is possible because photons interact through electromagnetism, and electromagnetism is strong enough to produce detectable changes in matter. A single photon can excite an electron in a detector. A single graviton, by contrast, interacts through gravity, and gravity is so weak that the equivalent detection event becomes fantastically unlikely. If photons were as shy as gravitons, photography would be a very disappointing hobby. The weakness also affects the sources. To detect individual particles, it helps to have a strong source that produces many of them, and a detector that can catch some fraction. We have abundant photon sources: lamps, stars, lasers, fires, screens, and occasionally the glowing eyes of a cat in a dark hallway, which is less a source and more a warning. We can create and manipulate photons easily. We can produce beams of particles in accelerators. We can detect neutrinos from nuclear reactors, the sun, supernovae, and the atmosphere. But gravitons cannot be produced and controlled in the same practical way. Any process that emits gravitational radiation does so very weakly unless huge masses move violently. The best sources are cosmic catastrophes such as colliding black holes and neutron stars. These events produce powerful gravitational waves, but they occur far away and cannot be arranged in a laboratory, which is probably for the best. One might ask whether we could use a particle accelerator to make gravitons. In principle, any energetic process involving matter has some gravitational interaction. But the probability of producing detectable gravitons in particle collisions is incredibly small in ordinary physics. Accelerators are excellent for probing electromagnetism, the strong force, the weak force, and the particles connected to those interactions. Gravity at those energies remains far too weak. To make gravity strong in a particle experiment, we would need energies associated with the scale where quantum gravity becomes important. Those energies are unimaginably beyond current machines. It is not a matter of needing a slightly larger accelerator around the next town. It would require a jump so vast that the phrase larger accelerator becomes almost comical. You would not build it in a country. You would start making uncomfortable comparisons to astronomical distances, and then someone would quietly close the budget meeting. This leads to the idea of the Planck scale, though we do not need formulas to understand the point. There is a tiny length and an enormous energy scale at which quantum effects of gravity are expected to become unavoidable. At ordinary energies, gravity is weak and smooth. At the Planck scale, space-time itself may no longer behave like a smooth background. It may fluctuate strongly or reveal a deeper structure. The problem is that reaching that scale directly is far beyond known experimental capabilities. We can observe the effects of quantum physics at atomic and subatomic scales. We can observe general relativity in planets, stars, black holes, and gravitational waves. But the place where both become equally loud is hidden at an extreme frontier. It is as if the universe put the answer in a locked drawer, then placed the drawer inside a mountain, then placed the mountain at the bottom of an ocean, on a planet orbiting another star. There are also background problems. If gravitons exist, the universe may be filled with them in many forms. There could be gravitons associated with gravitational waves from astrophysical events. There could be a faint background from the early universe. There could be quantum fluctuations related to gravity. But a detector would need to distinguish a single graviton from every other possible disturbance. This is not like looking for a rare bird in a quiet field. It is like looking for one specific, nearly invisible bird in a hurricane full of confetti, while the bird does not want to land and may pass through the binoculars without interacting. The problem is not merely sensitivity, it is identification. A claim detection would have to show that the signal could not have been caused by anything else. In physics, especially at the frontier, almost is not enough. A detector must persuade nature in public. Even gravitational waves themselves do not guarantee individual graviton detection. The waves observed from black hole mergers are very low frequency compared with many familiar quantum processes. Low frequency means each graviton in that wave, if we describe it quantum mechanically, would carry very little energy. The wave as a whole can be powerful because it contains an enormous number of quanta, just as a water wave can carry a lot of energy through the collective motion of many molecules. But one low-energy graviton would be extraordinarily hard to detect. Higher frequency gravitons would carry more energy individually, but known sources and detectors introduce other difficulties. Nature does not seem to provide a convenient graviton flashlight with an on switch, a focusing knob, and a polite instruction manual. There is another subtle problem. When a particle interacts strongly enough to be detected, the detection often changes the particle or absorbs it. For photons, this is normal. A photon hits a detector, is absorbed, and produces a measurable event. With gravitons, absorption is so unlikely that most simply pass through. If one were absorbed, the energy transfer might be so tiny that the detector could not reliably record it without being cooled, isolated, and controlled to a nearly impossible degree. Quantum measurement itself becomes part of the challenge. Every detector is made of matter, and matter is noisy at some level. Atoms vibrate, electrons fluctuate. The detector has its own quantum uncertainty. Asking it to register one graviton is like asking a sleeping person to notice a feather touching the roof of the house during a storm and then write down the time. This does not mean the graviton is scientifically useless. Direct detection is not the only way particles or ideas enter physics. Some particles were predicted before they were detected because they made sense of patterns. The neutrino was proposed to explain missing energy in radioactive decay long before it was observed. The Higgs boson was predicted because the theory required a field associated with particle masses, and it was found decades later. The graviton is different because the gap between prediction and direct detection may be much larger, perhaps permanently large. But the idea still helps physicists organize calculations, explore quantum gravity, and understand the weak field limit of any future theory. It is a guide even if it refuses to show its face. There may also be indirect evidence for the quantum nature of gravity one day. Instead of detecting a single graviton, experiments might test whether gravity can create quantum entanglement between small masses. If two objects become entangled through their gravitational interaction, that would suggest gravity has quantum features. Such experiments are extremely difficult, but they are more plausible than catching a lone graviton. Researchers may also look for subtle traces of quantum gravity in cosmology, black hole physics, or high-precision measurements of gravity at very small distances. The point is that finding the graviton directly is not the only possible route. Science often approaches the shyest truths indirectly, by noticing their footprints, shadows, and awkward effects on nearby furniture. The early universe is one of the most tempting places to search for clues. In the first moments after the beginning of cosmic expansion, gravity and quantum physics may have been deeply intertwined. Some theories suggest that primordial gravitational waves, produced in the very early universe, could leave an imprint on the cosmic microwave background, the ancient light left over from when the universe became transparent. Detecting such an imprint would not be the same as detecting individual gravitons, but it could provide evidence about quantum processes involving gravity. The challenge is that the signal, if it exists, is faint and can be confused with other astrophysical effects. The early universe does not hand us a clean photograph. It gives us a delicate pattern on ancient light, and then scatters dust, galaxies, and measurement difficulties in front of it, perhaps to keep us humble. Black holes may also offer indirect clues. They're governed by gravity, but quantum theory suggests they have temperature and can slowly radiate. This raises deep questions about information, entropy, and the microscopic structure of spacetime. If a complete quantum theory of gravity is found, it must explain black hole behavior. The graviton may appear in that theory in some limit, but the most important evidence may come not from single particles, but from understanding how black holes store and release information. A black hole is not a particle detector in the ordinary sense. It is more like a sealed exam paper from nature, written in curved space-time and thermodynamics, with some of the answers smudged. There is a philosophical lesson here, though it is a practical one too. The word particle can make us expect a thing that can be caught. We caught electrons in experiments. We detect photons. We infer quarks through scattering and the particles they form. We detect neutrinos with huge observatories. So when we hear graviton, we imagine that one day a machine will click and announce that one has arrived. Perhaps that will happen in some unexpected way, and it would be unwise to declare with perfect certainty that nature cannot surprise us. Nature has made a habit of surprising people who speak too firmly before breakfast. But based on what we currently understand, direct detection of a single graviton is so far beyond practical reach that many physicists treat it as effectively impossible. This creates a strange emotional position for the graviton. It is theoretically expected in many frameworks, but experimentally hidden. It is central to how we speak about quantum gravity in weak fields, but absent from our detectors. It belongs in textbooks as a hypothetical particle, yet it resists becoming an event on a screen. It is like a word in a language we can translate but not pronounce aloud. That does not make it meaningless. It makes it a reminder that reality is not obligated to make every layer accessible to the same methods. The universe can be understandable without being easy. It can offer patterns long before it offers direct sightings. The challenge also shows why gravity is so different from the other forces. The other interactions can be studied by isolating particles, colliding them, measuring their products, and building detectors that respond to their carriers. Gravity shapes everything, but its individual quantum effects are hidden because the force is so weak. On large scales, gravity dominates because mass accumulates, and because its attraction does not cancel out. On small scales, it becomes nearly impossible to separate from the noise. This reversal is one of the oddest facts in physics. The force that builds galaxies is the one whose single particle may be the hardest thing in the universe to catch. So when we say finding one is almost impossible, we mean several things at once. A graviton would interact extraordinarily weakly. A single one would carry very little energy in the gravitational waves we can observe. Practical detectors would be overwhelmed by noise. Making a detector large enough may create new gravitational problems of its own. Producing gravitons in controlled experiments is far beyond current energies. Natural sources are distant, faint in individual quantum terms, and difficult to isolate. And even if a signal appeared, proving it was truly one graviton would require excluding every ordinary explanation. Each obstacle alone would be serious. Together they form a wall so high that the wall itself may need its own planning permission. Yet this impossibility does not stop the search for quantum gravity. It changes the strategy. Physicists do not only wait for one graviton to bump into a detector. They study the behavior of gravitational waves, the nature of black holes, the early universe, the relationship between gravity and quantum information, and the possibility that tiny masses might reveal gravitational entanglement. They build better instruments, not always because those instruments will catch the graviton directly, but because every improvement gives us a clearer view of where gravity meets the rest of physics. The missing particle remains missing, but the search around it is rich. Sometimes a locked door teaches you the shape of the house. This is where the graviton becomes more than a particle. It becomes a test of how we know things. Must every real part of nature be directly detectable as an individual object? Or can some things be known through consistency, through collective effects, through the way theories fit together and explain what we observe? Physics prefers measurement whenever possible, but measurement has many forms. We do not see the interior of a black hole directly. We infer. We do not touch space-time curvature with a finger. We measure its effects. We do not see dark matter shining in a telescope. We track its gravity. The graviton may remain in this indirect category for a long time, perhaps forever. The question is whether future evidence can make its role unavoidable even without a single clean detection. For now, the graviton is almost perfectly quiet. If countless gravitons pass through the room, they do so without disturbing the air, the walls, the clock, or the thoughts settling slowly towards sleep. The Earth beneath you may be in a quantum description surrounded by an immense gravitational field whose deepest behavior would involve gravitons, but you feel only the smooth result. You feel weight, support, stillness. You do not feel individual quanta. And somewhere far away, black holes may collide, sending gravitational waves across space for millions or billions of years. Our detectors can hear the broad wave when it reaches us, a faint cosmic murmur from a violent event, but not the individual grains of the murmur. The graviton remains hidden inside the smoothness, like a single whisper inside a choir spread across the universe. That hiddenness naturally turns our attention to the places where gravity becomes loudest. If a single graviton is almost impossible to catch in a laboratory, perhaps the universe itself provides more extreme settings. Black holes, the early universe, and the violent birth and death of cosmic structures may not hand us gravitons one by one, but they may carry clues about what gravity is made of at the deepest level. To follow those clues, we have to look toward the darkest and earliest places we know, where space-time is stretched, compressed, heated and tested in ways no laboratory on Earth can easily reproduce. When the laboratory becomes too quiet to hear the graviton, the natural place to look next is the universe itself, not because the universe is tidy or cooperative, but because it contains conditions no experiment on Earth can easily reproduce. It has black holes, neutron stars, exploding stars, dense early fireballs, ancient radiation, and stretches of space where gravity has had billions of years to leave clues. If a single graviton is almost impossible to catch in a detector, then perhaps the best hope is not to catch one at all. Perhaps the best hope is to study the places where gravity becomes extreme, where space-time is shaken, stretched, compressed, and pushed close to the limits of what our theories can describe. The graviton may be hidden not like a coin under a rug, but like a faint detail in a much larger story, visible only through patterns left behind by the most powerful events in the cosmos. Black holes are the most obvious place to begin, because they are gravity made severe. They are not simply heavy objects. They are regions where mass has been compressed so tightly that space-time curves into a trap, cross the event horizon, and every future path leads inward. This does not mean a black hole is sucking in the universe like a cosmic drain with poor manners. Far from the black hole, its gravity can behave like the gravity of any other object with the same mass. But close to it, the geometry becomes extreme. Light can orbit. Time slows dramatically compared with faraway observers. Matter falling in is heated, stretched, and torn. The black hole becomes less like an object sitting in space, and more like a place where space and time have changed their rules. For a long time, black holes were treated mainly as predictions of general relativity. They were solutions to Einstein's theory, strange but mathematically serious. Over time, evidence for them grew. We found stars moving around invisible, massive objects. We observed powerful radiation from hot gas spiraling inward. We detected gravitational waves from black holes merging. We even produced images of the glowing material around supermassive black holes, where the dark central shadow revealed the presence of an event horizon. Black holes moved from theoretical oddities to observed astrophysical objects. They're real in the practical scientific sense, even if they remain deeply strange. The reason black holes matter for gravitons is that they bring gravity close to its most intense known behaviour. If gravity is quantum, then black holes should somehow be described by quantum gravity. Yet a black hole is also a triumph of smooth space-time geometry. General relativity describes its exterior beautifully. It tells us how objects fall, how light bends, how orbits behave, and how gravitational waves are produced when two black holes spiral together. But at the centre, the theory predicts a breakdown, a region where density and curvature become infinite in the mathematical description. Most physicists do not think nature truly makes infinities sitting inside black holes like little signs saying, "Theory ends here." Instead, they suspect that the classical theory is being pushed beyond its proper range. Quantum gravity should take over. If gravitons are the quanta of gravity, then black holes should involve them in some way. A black hole merger, for instance, releases an enormous amount of energy in gravitational waves. In a quantum description, those waves could be thought of as made of many gravitons. Not one or two, but an unimaginably large number acting together so smoothly that our detectors register a classical wave. When the wave passes Earth, it stretches and squeezes space by a tiny amount. The signal is not a single graviton knocking politely on the detector. It is the combined murmur of a vast gravitational disturbance, weakened by distance but still coherent enough to measure. This is one of the places gravitons might hide in plain sight. Every detected gravitational wave may correspond in the quantum language to a huge collection of gravitons. But because the number is enormous, and each individual quantum is far too weak to isolate, we hear only the collective sound. It is like listening to rain on a roof. You hear the rain fall as a texture, a steady noise, a changing pattern. You do not track one specific drop from cloud to tile to gutter. With gravitational waves, the problem is far more extreme. The individual quanta are so faintly interacting that even if the wave is real and measurable, the graviton inside the wave remains effectively unreachable. Still, gravitational wave astronomy is one of the best windows we have into strong gravity. Each black hole merger carries information about masses, spins, distances, and the behavior of spacetime under violent conditions. So far, the signals agree well with general relativity. That is important. It means Einstein's theory remains sturdy even when black holes collide. But scientists keep looking for tiny deviations. If the waves travelled at slightly different speeds depending on frequency, if their shapes carried unexpected echoes, if the final ringing of a black hole differed from prediction, those could be hints of new physics. Not necessarily direct evidence of gravitons, but possible signs that gravity has a deeper quantum layer. The final ringing of a black hole is especially interesting. After two black holes merge, the newly formed black hole settles down. It vibrates briefly, producing gravitational waves in a pattern sometimes compared to the ringing of a bell. The tones depend on the black hole's mass and rotation. In general relativity, a black hole is astonishingly simple from the outside. It is described by only a few properties. If future detectors measure these ringdowns with greater precision, they might test whether real black holes behave exactly as Einstein predicts, or whether quantum effects produce small corrections. If there are echoes or departures from the expected pattern, physicists would pay very close attention. They would also argue about it extensively, because that is how science digests surprises. Another black hole clue comes from Hawking radiation. Quantum theory suggests that black holes are not completely black. They should emit a very faint thermal radiation and slowly lose mass over enormous timescales. For large astrophysical black holes, this radiation is far too weak to detect directly. The black hole is colder than the surrounding cosmic background and absorbs more than it emits. But the idea itself is profound. It shows that when quantum fields are considered near an event horizon, black holes have temperature. They behave like thermodynamic objects. They have entropy. This connects gravity, quantum theory, and the physics of heat in a way that seems too deep to be accidental. Hawking radiation does not mean we have detected gravitons, but it suggests that space-time geometry and quantum fields are not separate stories. Something about horizons, information, and quantum effects is telling us that gravity must have microscopic degrees of freedom. Entropy usually counts hidden microscopic arrangements. If a black hole has entropy, what microscopic states does that entropy count? Are they states of space-time itself? Are they related to gravitons? Are they something more fundamental from which gravitons emerge only in gentle conditions? These questions are still open. Black holes hold them tightly. The black hole information problem makes the puzzle sharper. In ordinary quantum physics, information is not simply destroyed. The detailed state of a system may become scrambled beyond practical recovery, but the rules preserve it. Black holes appear to challenge this. Matter falls in. The black hole eventually radiates. If the radiation is purely thermal and carries no details about what formed the black hole, information seems lost. Many physicists believe information must somehow be preserved, but the mechanism remains a major problem. Solving it likely requires a quantum theory of gravity. The graviton may not be the whole answer, but any full answer must explain how gravitational degrees of freedom participate in storing and releasing information. Then there is the Big Bang, or more carefully, the early universe. The phrase Big Bang often makes people imagine an explosion happening at a point in empty space. That is not the best picture. It was not matter exploding into pre-existing emptiness. It was the expansion of space itself from an extremely hot, dense early state. As we look farther away in space, we look farther back in time, because light takes time to travel. The oldest light we can observe directly is the cosmic microwave background, a faint afterglow from when the universe became transparent. Before that, the universe was filled with hot plasma that scattered light constantly, like a fog made of charged particles. When it cooled enough for atoms to form, light could travel freely, and that ancient light still surrounds us. The early universe is important because it may have been a place where quantum gravity mattered. Today, the universe is mostly spacious and cold by comparison. Gravity is usually weak except near compact objects like black holes and neutron stars. But near the earliest moments we can imagine, density and temperature were enormous. If we run our current theories backward, we reach a point where general relativity suggests a singular beginning. As with black holes, most physicists suspect that this singularity is not a physical object, but a sign that the theory is incomplete. A quantum theory of gravity should describe what happened when the universe was so young and dense that spacetime itself could not be treated as a smooth classical stage. Could gravitons from the early universe still be around? In principle, yes. If gravity is quantum, the early universe could have produced a background of primordial gravitons, a kind of ancient gravitational radiation. But detecting such a background is incredibly difficult. It would not show up as little particles striking a detector one by one. Instead, it might leave indirect traces, especially in the polarization patterns of the cosmic microwave background, or in a faint gravitational wave background spread across the sky. These traces would be extremely subtle. They can be confused with dust, foreground galaxies, instrumental effects, and other sources of cosmic noise. The universe has written its early history on a very old page, and then placed that page behind several layers of smudged glass. One major idea connected to the early universe is inflation. According to inflationary models, the universe underwent a brief period of extremely rapid expansion very early on. This idea helps explain why the observable universe is so uniform on large scales and why its geometry appears close to flat. Inflation also predicts that quantum fluctuations in the early universe could have been stretched to cosmic size. Tiny quantum variations became seeds for galaxies and clusters. In many versions of inflation, quantum fluctuations of the gravitational field would also be stretched, producing primordial gravitational waves. In a quantum description, those waves would be related to gravitons. If such primordial gravitational waves are ever detected, they would give us a rare glimpse of gravity behaving quantum mechanically in the early universe. It would not be the same as catching a single graviton in a box, but it would be strong evidence that quantum fluctuations of space-time existed and were amplified into cosmic signals. That would be extraordinary. It would mean that the largest structures we observe may carry traces of tiny quantum events from the earliest moments. The universe would be using the sky as a recording surface, and physicists would be trying to play back the faintest track without scratching the record. Neutron stars are another place where gravity becomes intense, though not as extreme as black holes. A neutron star is the collapsed core of a massive star, packed so densely that matter is compressed beyond ordinary atomic structure. A spoonful of neutron star material would have a mass beyond anything household furniture should be asked to support. Neutron stars can spin rapidly, have strong magnetic fields, and sometimes collide with one another. When two neutron stars merge, they produce gravitational waves, intense light, and heavy elements such as gold and platinum. These events are valuable because they combine strong gravity with matter under extreme conditions. Unlike black hole mergers, neutron star mergers involve material that can shine, explode, and reveal details through both light and gravitational waves. Gravitons are not likely to be caught individually from neutron star mergers either, but such events test gravity and nuclear physics together. The gravitational wave signal depends on how the neutron stars deform as they approach one another. That deformation depends on the strange dense matter inside them. By studying the waves, physicists can learn about both gravity and matter at extremes. If there are deviations from general relativity or signs of additional gravitational behaviour, they may appear in such systems. Again, the graviton hides not as a single click in a detector, but as part of a pattern. The same is true of the gravitational wave background from many distant sources. Across cosmic history, black holes and neutron stars have been merging. Their signals overlap into a faint background hum. Future detectors may map this background more clearly. Some part of it may come from ordinary astrophysical sources. Another part, if we're fortunate, could come from processes in the early universe. The challenge is to separate the ingredients. It is like hearing a room full of conversations from another floor and trying to determine whether one voice belongs to someone from the beginning of time. Difficult, yes. A little absurd, also yes, but not impossible in principle. There are other possible hiding places in theory. Some models suggest that the early universe could have produced high-frequency gravitational waves. Others explore cosmic strings, hypothetical defects in space-time that could create gravitational radiation. Some ideas involve extra dimensions, where gravity might behave differently at small distances or high energies. Some proposals suggest that quantum gravity effects could leave tiny imprints in the distribution of galaxies or in the behaviour of black holes. None of these are confirmed routes to gravitons, and many may turn out to be wrong, but they show the range of places physicists look when direct detection is unavailable. The search spreads outward, not because the answer is everywhere, but because gravity touches everything. It is worth being careful with the phrase "where gravitons hide." If gravitons exist, they are not hiding with intention. They are not shy little creatures avoiding appointments. They are hard to observe because their interactions are weak, and because the conditions that reveal quantum gravity are extreme. The hiding places are really physical regimes where their effects might matter more, or where the quantum nature of gravity might leave indirect evidence. Black holes, the early universe, gravitational waves, and dense stars are not graviton traps. They're environments where the smooth classical picture is pushed hard enough that deeper structure may show. The Big Bang and black holes are also linked in a conceptual way. Both involve situations where general relativity, followed too far, leads to singularities. In a black hole, the singularity lies inside the event horizon. In the early universe, the singularity appears when we trace expansion backward to an initial limit. In both cases, the appearance of a singularity is a warning. It tells us the equations are being asked questions outside their range. A complete quantum gravity theory should smooth out or replace these singular descriptions with something physically meaningful. Whether that involves gravitons as fundamental particles or as emergent ripples is one of the open questions. A future theory might say that near ordinary weak gravity, gravitons are perfectly valid. They describe quantum ripples in nearly flat space-time. But near singularities, the notion of a graviton may no longer be enough. The whole idea of a particle depends on having a background where particle states can be defined. In wildly fluctuating space-time, the particle picture can break down. This is not a failure of the graviton idea. It is a reminder that concepts have domains. A wave on the sea is clear when the sea is recognizable. If the sea itself turns into foam at every scale, the word wave needs help. This is why black holes are not just sources of gravitational waves, and the early universe is not just a possible factory for ancient gravitons. They are testing grounds for the meaning of space-time. They force us to ask whether space and time are fundamental or emergent. They ask what happens to information when geometry becomes extreme. They ask whether the smooth curves of Einstein's theory are built from quantum ingredients. The graviton may be one of those ingredients, or it may be the low-energy sign of a deeper structure. Either way, these cosmic settings are where the question becomes unavoidable. For now, the evidence we have is mostly classical. Gravitational waves behave as general relativity predicts. Black hole images match the broad expectations of curved space-time. The cosmic microwave background supports a hot early universe and gives detailed information about cosmic structure. None of this directly reveals a graviton, but each observation narrows the possibilities. Each one tells us which theories survive contact with reality. That is how physics often moves, not by one grand revelation, but by a long narrowing of paths. Some doors close quietly, others remain open. A few begin to glow around the edges. As detectors improve, the search will become more refined. Ground-based gravitational wave observatories will become more sensitive. Space-based detectors may listen to lower frequency waves from massive black holes and other sources. Cosmic microwave background experiments will keep searching for ancient gravitational wave patterns. Pulsar timing arrays, which use the steady signals from rotating neutron stars, may reveal gravitational waves with wavelengths measured across light years. These approaches will not place a single graviton in a jar, but they may reveal more about the quantum history of gravity than direct detection ever could. Sometimes the best way to study a whisper is not to catch the breath that made it, but to listen to how the room responds. There is something fitting about this. Gravity is the force that acts most clearly through relationships. It shapes paths, distances, clocks, and structures. It is known through motion and curvature, through falling and orbiting, through bending light and rippling space-time. So perhaps its quantum nature will also be known through relationships, through patterns in ancient radiation, through correlations in gravitational wave backgrounds, through the information stored in black holes, through the way small masses might become entangled by their mutual attraction. The graviton, if it is ever confirmed, may arrive not as a single dramatic particle event, but as the unavoidable interpretation of many connected clues. Black holes and the Big Bang therefore do not give us an easy hiding place to search with a flashlight. They give us a set of questions sharpened by extremes. What happens when gravity becomes so strong that space-time traps light? What happened when the universe was so dense that our current theories cannot reach further back? What is the microscopic meaning of black hole entropy? Did quantum fluctuations of gravity seed ancient gravitational waves? Can the smooth geometry we observe be built from quantum pieces? These questions all point toward quantum gravity, and the graviton stands near the entrance as the simplest particle-shaped clue. The room may still feel calm while thinking about this. The floor remains steady. The blanket has not become a black hole. The universe outside the window appears quiet, but far away black holes merge and send waves through space-time. In every direction, ancient light carries traces of the early universe. In dense stars, matter is pressed into forms we cannot make on Earth. At the edge of every known theory, gravity keeps asking to be understood more deeply. The graviton may be hidden in the collective waves from cosmic collisions, in the faint fingerprints of inflation, in the thermodynamics of horizons, or in the low energy limit of a theory we have not yet completed. And that leads naturally to the next layer of the search, where physicists stop asking only where the graviton might be found, and start asking what kind of deeper framework could make gravity quantum in the first place. The search for gravitons leads into a wider search for quantum gravity, and this is where the story becomes both more technical and more uncertain. We have a successful theory for gravity on large scales, general relativity, where matter and energy curve space-time and objects move along the paths that curvature allows. We also have a successful theory for the small world, quantum physics, where fields come in quanta, uncertainty is built into measurement, and particles are understood as excitations of deeper fields. Each theory works brilliantly in its own proper setting. Together, however, they create a problem. When gravity is weak and the quantum effects are ordinary, we can keep them mostly separate and life goes on. Stars shine, phones work, apples fall, and nobody has to solve the deepest problem in physics before making tea. But in places where gravity is extremely strong and quantum effects cannot be ignored, such as the centre of black holes or the earliest moments of the universe, the two languages begin to clash. This clash does not mean that either theory is simply wrong. It means they are incomplete when pushed into a shared extreme. General relativity treats space-time as smooth. Quantum physics tells us that fields fluctuate, that empty space is not truly empty, and that nature at small scales is not smooth in the everyday sense. If space-time itself is part of the physical world, then it is natural to ask whether it too should have quantum behaviour. Does distance fluctuate? Does time become uncertain? Is there a smallest meaningful scale? Can geometry itself be made from something more basic? These are not decorative questions added for drama. They appear because the known theories leave gaps exactly where the universe becomes most extreme. The graviton is one way into this problem. In a weak gravitational field, where space-time is almost flat, physicists can treat gravity like a small disturbance and apply quantum thinking to that disturbance. The result is the graviton, a hypothetical quantum ripple of the gravitational field. This works as a low-energy idea. It tells us what a quantum of gravitational radiation would look like in calm conditions. But it does not give a full theory of quantum gravity. It is a little like understanding small ripples on a pond while still not knowing what happens when the pond, the shore, the measuring stick, and the idea of water all begin to shake at once. The graviton may be real as a useful particle in ordinary weak gravity, but the deeper layer may not be made simply of gravitons arranged like tiny bricks. String theory is one of the most famous attempts to find that deeper layer. Its basic proposal is surprisingly simple to state, even though the mathematics behind it is anything but simple. Instead of treating the most fundamental things as point-like particles, string theory suggests that they are tiny one-dimensional strings. These strings can vibrate in different ways. Different vibration patterns appear to us as different particles. One vibration might look like an electron, another might look like a photon, another might look like a quark. The idea is that what we call particles are not separate basic objects, but different notes played by the same kind of tiny string. It is a neat image, although one should be careful not to picture little violin strings floating in space, because nature is rarely kind enough to provide such comfortable furniture for the mind. The reason string theory became so important to quantum gravity is that it naturally includes a particle with exactly the kind of properties expected of the graviton. In the theory, one of the string vibration modes behaves like a massless particle with spin 2. That is precisely what a graviton should be in the usual quantum description. This was not a small detail. It meant that a theory built from strings did not have to force gravity in afterward as an awkward extra. Gravity appeared from the structure of the theory itself. For many physicists, this was a deeply compelling sign. It suggested that the graviton might not be an isolated missing particle, but part of a broader framework where all particles and forces arise from the same underlying object. Another appealing feature of string theory is that strings are not point-like. In ordinary particle physics, particles are treated as having no size. That point-like nature can create mathematical infinities when gravity is quantized in a straightforward way. In simple terms, interactions at exactly zero distance become too violent for the calculations to behave. Strings soften this problem because interactions are spread over a tiny length, rather than concentrated at a point. The string has extension. It is still unimaginably small, but not point-like. This spreading can make the theory better behaved at extremely short distances. It offers a way to avoid some of the infinities that appear when physicists try to quantize gravity using the same methods that work for the other forces. String theory also suggests that there may be more dimensions of space than the three we experience in everyday life. That idea can sound extravagant, as if physics has opened a cupboard and found several extra directions folded behind the towels. But in the theory, extra dimensions are not added for fun. They are required for mathematical consistency. If they exist, they may be curled up so tightly that we do not notice them at ordinary scales. Imagine an ant walking along a very thin wire. From far away, the wire looks like a one-dimensional line, but the ant can also move around the wire's tiny circular thickness. A hidden dimension can be real, but too small to notice directly. In string theory, the extra dimensions would be far smaller than anything current experiments can probe. These extra dimensions create both richness and difficulty. The way they're shaped can influence the particles and forces we observe. Different shapes can lead to different possible low-energy physics. This gives string theory an enormous landscape of possible versions. In one sense, that is powerful, because the theory has many ways to connect with the kind of universe we observe. In another sense, it is a problem, because if there are too many possible solutions, it becomes hard to make clear predictions. A theory becomes scientifically strongest when it tells us not only what can happen, but what must happen. String theory has produced deep mathematical insights and important connections across physics, but it has not yet given a unique, experimentally confirmed description of our universe. One of the most influential ideas to emerge from string theory is holography. The basic notion is that a theory with gravity in a volume of space can sometimes be equivalent to a theory without gravity on the boundary of that space. This sounds almost unreasonable at first. It is like saying that everything happening inside a room could be fully described by information written on the walls. Yet in certain mathematical settings, this relationship appears to work. Holography has given physicists powerful tools to study black holes, quantum information, and the relationship between gravity and quantum theory. It suggests that space-time itself may not be fundamental in the way we usually imagine. It may emerge from quantum information arranged in a lower dimensional description. This matters for gravitons because it changes the question. If space-time emerges from something deeper, then the graviton may also emerge. It would not be the most basic building block of nature. It would be a low-energy ripple of an emergent space-time, the way sound waves are ripples in air rather than fundamental particles of the universe. This does not make the graviton fake. Sound is real. Waves are real. But they are not the deepest layer. Holography hints that gravity might be similar. It may arise from quantum relationships that do not look gravitational at first. The smooth geometry of space-time could be the large-scale result of quantum entanglement and information. The idea that space-time might emerge from entanglement has become one of the most active and fascinating directions in theoretical physics. Entanglement is a quantum connection between systems, where the state of one cannot be fully described without the other, even when they are separated. In some modern approaches, the pattern of entanglement may help build the shape of space. Regions that are strongly entangled may behave as if they are close together. Regions with less entanglement may behave as if they are farther apart. This is not yet a complete theory of our universe, but it suggests a radical possibility. Space may not be the container in which quantum things live. Space may be constructed from the relationships among quantum things. If that is true, gravity may be less like a force added to a pre-existing stage, and more like a large-scale rule that appears when the underlying quantum network is viewed from far away. That would fit the idea that general relativity is an emergent description, extraordinarily accurate at large scales, but not fundamental at the deepest level. The graviton would then be a small vibration of this emergent geometry, not a tiny object sitting at the bottom of everything. It would be important, but not final. In this view, asking what the graviton is might be like asking what a wave is before understanding water molecules. The wave is real, measurable, and meaningful, but the deeper explanation lies beneath it. String theory is not the only path. Another major approach is loop quantum gravity. While string theory often begins with quantum objects and tries to include gravity naturally, loop quantum gravity begins more directly with general relativity and attempts to quantize space-time geometry itself. In this approach, space is not smooth at the smaller scales. Instead, it has a kind of discrete structure, often described through networks of relationships. areas and volumes may come in tiny quantum units, not because space is made of little cubes in a simple sense, but because geometry has quantized properties. The smooth space of experience would then be an approximation, like the smooth surface of a table that is actually made of atoms when viewed closely. Loop quantum gravity does not start by placing gravitons on a fixed background spacetime. In fact, one of its goals is to avoid relying on a fixed background at all. This is called background independence, though the phrase is more technical than soothing. The point is simple enough. General relativity teaches that spacetime is dynamic. It responds to matter and energy. So a quantum theory of gravity should not assume a fixed spacetime stage from the beginning. It should describe geometry itself as quantum. That makes the theory conceptually close to Einstein's insight, but it also makes the mathematics difficult. If there is no fixed background, even defining ordinary particle states becomes harder. In loop quantum gravity, gravitons should still appear in the right limit if the theory is correct. After all, any successful quantum gravity theory must reproduce known physics when gravity is weak and space-time looks smooth. It must give us gravitational waves, the predictions of general relativity, and the expected low-energy quantum behavior. So the graviton may emerge from loop quantum gravity as an approximate excitation of a deeper quantum geometry. But the starting point is not the graviton. The starting point is the quantization of geometry itself. This shows again that the graviton can be a valuable clue without being the deepest object. There are other approaches too. Asymptotic safety explores the possibility that gravity, when treated as a quantum field theory, may become well behaved at extremely high energies, because it approaches a special kind of stable behavior. Causal dynamical triangulations attempts to build space-time from simple building blocks while preserving a sense of cause and effect, then studies whether smooth space-time emerges at large scales. Causal set theory suggests that space-time may be fundamentally discrete, made of elementary events ordered by causality. Other ideas explore emergent gravity, where gravity arises from thermodynamics, entropy, or information rather than being fundamental. Each approach has strengths, challenges, and unanswered questions. None has yet won by delivering a complete theory confirmed by decisive experiment. This variety can make the search feel messy. People often like science stories where there is one great theory waiting to defeat all rivals, perhaps while dramatic music plays and someone writes on a chalkboard very quickly. Real theoretical physics is usually less tidy. Different ideas illuminate different parts of the problem. String theory has given extraordinary insights into quantum gravity, black holes, and mathematical physics. Loop quantum gravity has sharpened the question of quantum geometry and background independence. Holography has changed how physicists think about space-time and information. Other programs explore whether gravity can remain a quantum field theory under special conditions, or whether space-time is fundamentally discrete. The field is not a single road. It is a mountain range with several paths upward, and from below it is not always clear which one reaches the summit. Experiment is the great difficulty. A theory of quantum gravity must explain things we already know, but it must also eventually say something testable beyond them. The problem is that quantum gravity effects are expected to be extremely tiny in ordinary settings, and most dramatic in places we cannot easily access. We cannot build a black hole in a laboratory and politely ask it about information. We cannot recreate the first instant of the universe on a workbench, which is probably just as well, considering how difficult it is to clean up after ordinary experiments. We cannot reach the energies where space-time may reveal its smaller structure, so physicists look for indirect windows, gravitational waves, black hole thermodynamics, cosmological signals, precision tests of gravity at short distances, quantum experiments with tiny masses. Each is difficult, but each may offer a clue. One promising direction involves testing whether gravity can mediate entanglement between small objects. If two tiny masses become entangled through their mutual gravitational attraction, that would suggest that gravity itself has quantum features. It would not detect a graviton directly, but it could show that gravity cannot remain purely classical while interacting with quantum systems. These experiments are extremely challenging because the gravitational interaction between small masses is weak, and the objects must be isolated from other sources of entanglement and noise. Still, the idea is exciting because it brings quantum gravity questions closer to laboratory scale. It asks not for a black hole or a particle accelerator the size of a solar system, but for exquisite control of small systems. That is still very hard, but at least it fits inside a building. The deeper search also affects how we think about the word particle. In the standard model, particles are excitations of fields on spacetime. In quantum gravity, spacetime itself may be part of what must be explained. If spacetime is emergent, then particles, including gravitons, may only be meaningful after that emergence has taken place. This does not mean particle physics is wrong. It means it may be a highly accurate layer of description. A map of roads is not wrong because it does not show the mineral structure of the asphalt. It is right for navigation. In the same way, photons, electrons, and gravitons may be right descriptions at one level, while a deeper description uses different ingredients. String theory, loop quantum gravity, holography, and other approaches all share one requirement. They must recover the world we observe. They must explain why general relativity works so well. They must explain why quantum field theory works so well. They must not break the successful physics of planets, atoms, light, and gravitational waves. A deeper theory cannot simply be strange. It must be strange in a way that becomes familiar physics when viewed from the right distance. That is a severe demand. It is easy to invent wild ideas. It is much harder to invent wild ideas that quietly turn into the measured orbit of Mercury, the bending of starlight, the spectrum of atoms, the behavior of particle collisions, and the signals from black hole mergers. This is why the graviton remains useful even in theories where it is not fundamental. It is a checkpoint. In any successful quantum gravity theory, if we look at weak gravitational waves travelling through nearly flat space-time, we should recover something that behaves like gravitons. If a proposed theory cannot produce the familiar low-energy behavior of gravity, it is in trouble. The graviton is like a door that the deeper theory must pass through on its way back to ordinary physics. It may not be the basement of reality, but it is part of the staircase. There is a quiet lesson in all of this. The search for quantum gravity is not only about adding gravity to the particle list. It is about understanding whether space and time themselves are fundamental or emergent. It is about whether the smoothness of geometry is a large-scale illusion, whether black hole entropy counts microscopic states, whether the beginning of the universe can be described without singularities, and whether the most familiar force in human experience comes from quantum information, tiny strings, discrete geometry, or a principle still waiting to be recognized. The graviton is the simplest way to ask the question, but the answer may be larger than the particle. For the listener settling deeper into rest, perhaps the comforting part is that uncertainty here is not emptiness. It is not that physicists know nothing. They know a great deal. They know how gravity behaves across the solar system and around black holes. They know how particles behave in accelerators and atoms. They know that any deeper theory must respect both. They know what a graviton should look like in the low energy limit. They know why it is hard to detect. They know where the old theories begin to strain. The unknown is not a blank wall. It is a detailed outline with several missing rooms. And so, the deeper layer remains out of reach but not out of thought. It may be made of strings vibrating in hidden dimensions. It may be a network of quantized geometry. It may be encoded holographically, with gravity emerging from information on a boundary. It may be a theory where space-time grows out of entanglement, or where gravity becomes safe at high energies, or where cause and effect are the basic building blocks. Some of these ideas may survive, some may fade, some may turn out to be approximations to something even more surprising. That is not a weakness of the search. It is how difficult questions are approached when the universe refuses to answer in one sentence. The graviton then sits in the middle of the story like a small but important clue. If found in theory, it tells us gravity can speak the quantum language. If never detected directly, it still marks the place where that language should meet observation. In string theory, it appears naturally as a vibration. In other approaches, it may emerge from quantum geometry or information. In every serious approach, the smooth space-time of Einstein must somehow arise from something that can live peacefully with quantum physics. The missing particle of gravity is not just missing from a detector, it is missing from our final understanding of what space, time and matter really are. And once we have followed the search this far, the final question becomes less about whether one tiny graviton can be caught and more about what it would mean for science and for our picture of reality if gravity's quantum nature were finally confirmed. Imagine for a moment that tomorrow morning, somewhere in a quiet laboratory or hidden inside the data from a distant cosmic event, physicists found evidence that could only be explained by the graviton, not a vague hint, not a maybe. Not one of those scientific situations where everyone squints politely at a graph and says it is interesting, which often means nobody is sleeping well for the next 3 years. Imagine a clear result. Gravity has a quantum particle. The missing messenger is real. The graviton, long predicted in theory and long hidden from experiment, has finally stepped into the world of evidence. What would that actually mean? The first thing it would mean is not that Einstein was wrong. This is important, because science is often described as if every new idea arrives with a tiny hammer to smash the old one. But the history of physics is usually more subtle. Einstein did not destroy Newton. He showed that Newton was an excellent approximation in the right conditions. Newton still works for falling objects, orbiting planets, bridges, baseballs, and the general tragedy of dropping toast butter side down. Einstein gave us a deeper layer, especially where gravity is strong or motion is fast. In the same way, finding the graviton would not throw general relativity away. It would place general relativity inside a broader quantum picture. The smooth curvature of space-time would still be real at large scales. Black holes would still curve light. Clocks would still tick differently in different gravitational fields. Gravitational waves would still travel across the universe. But underneath that smooth description, we would know there is a quantum structure. That would be a major shift. General relativity describes gravity as geometry. Matter and energy shape space-time, and space-time guides motion. Quantum theory describes nature in terms of fields, quanta, probabilities and interactions. These two languages have both succeeded so well that the problem is not choosing which one is good and which one is bad. The problem is that they both seem necessary. Finding the graviton would show that gravity can, at least in some setting, speak the quantum language directly. It would confirm that gravitational radiation is not only a smooth ripple in space-time, but also comes in quantum units. A gravitational wave could then be understood as a collective state made from many gravitons, just as a beam of light can be understood as many photons acting together. That confirmation would answer one question while opening several more. If the graviton were detected, physicists would immediately ask what kind of detection it was. Was it a direct observation of a single graviton, which would be astonishing beyond measure? Was it an indirect signal showing that gravity can produce quantum entanglement? Was it evidence from the early universe, where quantum fluctuations of gravity left a pattern in ancient radiation? Was it a feature in black hole physics that could not be explained without quantum gravitational degrees of freedom? The meaning would depend on the kind of evidence, but in every case, the basic result would be the same. Gravity is not purely classical, it has quantum behavior. A direct detection of a single graviton would be the most dramatic version, though it is also the least expected with anything like current technology. If it happened, it would mean that physicists had found a way around difficulties that now look almost impossible. A single graviton interacts so weakly that most of them would pass through a detector, through Earth, and through entire stars without leaving a trace. To register one cleanly, would require a detector of extraordinary sensitivity and a method for excluding every other possible source of noise. Such a discovery would not merely add one particle to a list, it would force a rethinking of what is experimentally possible. It would be like discovering that a whisper from across the universe can be heard after all, not because the whisper became loud, but because someone learned how to make the room silent enough. More likely, evidence for the graviton or for quantum gravity would come indirectly. That would still be powerful. Physics often accepts things through patterns before direct handling becomes possible. We do not see space-time curvature with our eyes, but we measure its effects. We do not watch dark matter shine, but we infer its presence from gravity. We do not look inside a black hole, but we learn about it from the motion and radiation around it. If experiments showed that gravity can entangle two quantum systems, that would be a profound result. Entanglement is not a classical feature. If gravity can mediate it, then gravity must carry quantum information in some form. That would not necessarily prove that a particle called the graviton had been caught like a moth in a jar, but it would strongly suggest that gravity has quantum degrees of freedom. The graviton would become part of the necessary language for weak gravitational interactions. If the evidence came from gravitational waves, it might appear as tiny deviations from the predictions of classical general relativity. Future detectors may listen to black hole mergers with much greater precision. They may study the ringing that follows a merger, the background hum of many distant sources, or low-frequency waves from massive black holes. If those waves showed a pattern that required quantized gravity, physicists would have a new kind of window. The discovery would not be a small click in a particle counter. It would be a structure in the music of space-time. The universe would not hand us one graviton. It would show us that the whole wave has a quantum score written beneath the smooth sound. If the evidence came from the early universe, the meaning would be just as deep. In the first moments of cosmic history, quantum fluctuations may have been stretched to enormous scales. Some of those fluctuations may have involved gravity itself. If primordial gravitational waves were detected in a way that clearly pointed to quantum gravitational origins, we would be seeing traces of the universe when it was young enough for gravity and quantum physics to be inseparable. That would not be a laboratory detection in the usual sense. It would be archaeology of space-time. The evidence would come from ancient light, from patterns across the sky, from signals that have travelled since the universe first became transparent. It would mean the sky itself carries a record of gravitons or quantum gravitational waves from near the beginning. Such a discovery would change the status of quantum gravity from a theoretical necessity to an experimental science. Right now, quantum gravity is driven by strong reasoning, mathematical consistency, black hole puzzles, cosmology, and the need to unite our best theories. But it lacks the kind of decisive experimental anchor that particle physics gained from discoveries like the photon, the neutrino, and the Higgs boson. Finding evidence for the graviton would provide that anchor. Theories could no longer float only on elegance or internal consistency. They would have to explain the observed quantum behavior of gravity. Some ideas would survive, others would fail. The field would become more constrained, and that is a good thing. In science, a theory that can be ruled out is often more useful than one that can fit anything after enough adjusting. It would also change how we think about space-time. If gravitons exist, then space-time is not merely a smooth background. At least in weak fields, it has quantum excitations. The geometry of the universe would have a grainy side, though not necessarily grainy like sand or pixels in a simple picture. We would know that the smooth stage of general relativity can vibrate in quantum units. This would make space-time feel less like a fixed container and more like a physical system with its own microscopic behavior. Distances, durations, and curvature would no longer be only classical features. They would be large-scale expressions of something quantum underneath. But finding the graviton would not automatically solve every mystery. It would be a beginning, not a finish line. We could detect evidence of gravitons and still not know the complete theory of quantum gravity. A single particle does not explain the whole structure. When the photon became central to quantum theory, physicists still needed quantum electrodynamics to describe its interactions fully. When the Higgs boson was found, it confirmed the Higgs field, but it did not answer all questions about mass, dark matter, or why the particles have the values they do. In the same way, a graviton discovery would confirm an essential piece, but it would not immediately tell us what happens at the centre of a black hole, or before the earliest describable moment of the universe. It would give us a foothold on the mountain, not a helicopter to the summit, though many graduate students would probably accept the helicopter. The discovery would sharpen the competition among theories. String theory would gain support if the graviton appeared with properties matching its expectations, especially since a massless spin 2-particle arises naturally in that framework. But other theories also expect gravitons or graviton-like excitations in the low energy limit. Loop quantum gravity, emergent gravity, asymptotic safety, holographic approaches and other ideas would all need to show how they produce the observed behaviour. The important question would not simply be whether a theory contains the word graviton. It would be whether it correctly predicts the detailed properties, interactions and limits of the evidence. Science is not impressed by name tags alone. The particle has to behave. If the graviton were found to have unexpected properties, the impact would be even greater. Suppose it did not behave exactly as the simplest theory predicts. Suppose gravitational waves showed tiny signs that the graviton has a minuscule mass, or that gravity changes at enormous distances, or that space-time has a subtle structure not captured by current models. That would be revolutionary. It could point toward extra dimensions, new fields, modifications of gravity, or a deeper quantum architecture. Of course, extraordinary claims would require extraordinary evidence. Physicists would test, repeat, argue, refine, and probably drink alarming amounts of coffee. But if the evidence held, it could reshape not only quantum gravity, but cosmology as well. There would also be implications for black holes. A quantum theory of gravity should explain black hole entropy, Hawking radiation, and the information problem. Finding the graviton would not automatically solve these issues, but it would confirm that the gravitational field has quantum states. That would strengthen the idea that black holes must have microscopic gravitational degrees of freedom. It would support the search for how information is stored and released. It would make it harder to treat space-time geometry as merely classical in situations involving horizons. The black hole would become even more clearly a quantum object, not just a dark region described by geometry. For cosmology, the discovery could help us understand the beginning of structure. If primordial gravitons or quantum gravitational waves were confirmed, then the large-scale universe would carry direct evidence that quantum effects shaped cosmic history. The galaxies we see today may have grown from tiny early fluctuations. If gravity itself contributed quantum fluctuations, then gravitons would be connected not only to black holes and waves, but to the origin of cosmic structure. The missing particle of gravity would not be some isolated laboratory curiosity. It would be part of the story of why the universe has galaxies, clusters, and the vast web of matter spread across space. Would finding the graviton lead to new technology? Eventually, perhaps, but not in the simple way people sometimes imagine. The discovery of quantum mechanics led to lasers, transistors, magnetic resonance imaging, atomic clocks, and modern electronics, but many of those applications came decades after the basic science. A graviton discovery would probably not lead quickly to gravity radios, anti-gravity boots, or a convenient household black hole for waste disposal, which would be a terrible idea in several departments. Because gravity is so weak, controlling gravitons would be far harder than controlling photons. We can make light beams because electromagnetism is easy to manipulate compared with gravity. Making a practical graviton device may remain impossible. The greatest immediate effect would be on understanding, not gadgets. That said, understanding can change technology in ways nobody predicts. When early scientists studied electricity, they were not designing smartphones. When quantum theory began, it was not obvious that it would become the foundation of electronics. If quantum gravity became experimentally accessible, new measurement techniques, new sensors, and new ways of controlling delicate quantum systems might follow. The path from deep theory to practical use is usually indirect. It wanders. It takes time. It occasionally gets lost and returns with something useful in its pockets. But the first meaning of finding the graviton would not be commercial. It would be conceptual. We would understand nature more deeply. It would also change the emotional map of physics. The divide between the very large and the very small has been one of the great tensions of modern science. General relativity rules the cosmic scale. Quantum theory rules the microscopic scale. Human beings live in the middle, where both are usually quiet enough that breakfast can proceed normally. Finding the graviton would show that the divide can be crossed. It would be evidence that the force shaping galaxies also belongs to the quantum world. The same universe that makes electrons uncertain and photons discrete also makes space-time ripple in quanta. The gap would not close completely, but a bridge would stand where there had long been fog. There is something humbling about that. Gravity is the first force we feel, and the last one we have been able to fit into the quantum picture. A baby learns gravity before language, before numbers, before any idea of planets or space-time. Drop a toy and the lesson begins. Yet the deepest explanation of that same familiar falling has led through Newton, Einstein, black holes, gravitational waves, quantum fields, and the missing graviton. The most ordinary experience points toward the hardest theory. That is one of the quiet pleasures of physics. It takes the obvious and reveals that it was never obvious at all. If the graviton were found, it would also remind us that invisibility is not the same as unreality. For a long time, many things in physics existed first as necessities in thought, then as faint signatures, then as confirmed parts of nature. Atoms, neutrinos, gravitational waves, and the Higgs boson all followed paths where theory and evidence slowly met. The graviton may follow a stranger and harder path, perhaps never appearing as a single directly detected particle, but if its effects were confirmed, it would join that tradition. It would show that patience, mathematics, experiment, and imagination can reach into places far beyond ordinary perception. At the same time, the discovery would not make the universe less mysterious. It might make it more mysterious in a better way. Good discoveries do not simply close questions, they make the next questions clearer. If gravitons exist, what is the full theory that contains them? Are they fundamental, like electrons seem to be, or emergent, like sound waves in a material? Does spacetime have atoms of geometry, strings, networks, or information-based structure underneath? How do gravitons behave near black holes? What happened when the universe was so young that gravitons, spacetime, and quantum fields were part of one extreme state? A confirmed graviton would be an answer that behaves like a doorway, and perhaps that is the most honest meaning. Finding the graviton would tell us that gravity has a quantum face. It would confirm that the smooth geometry of Einstein is not the whole story. It would give quantum gravity experimental ground to stand on. It would connect gravitational waves to particle physics, black holes to quantum information, and the early universe to the smallest possible ripples of space-time. It would not give us control over gravity. It would not make science complete. It would not remove the strangeness. But it would show that one of the deepest missing links in physics is real. As this quiet journey settles back into the room around you, gravity is still doing what it has done all along. It holds you gently against the Earth. It keeps the moon in its path. It gathers stars into galaxies and galaxies into larger structures. It bends light and slows time and carries waves from black hole collisions across the dark. If the graviton exists, then beneath all of that smooth and steady behavior, there is a quantum whisper, too faint for ordinary instruments, too subtle for the senses, but perhaps written into the deepest workings of reality. The missing particle of gravity would not make gravity less familiar, it would make the familiar deeper. The weight of a blanket, the fall of rain, the orbit of a planet, and the trembling of space-time would all belong to one larger story, where the universe is not divided between the cosmic and the quantum, but woven from both. And wherever you're listening from tonight, whatever time your clock happens to show, that same gravity is present with you now, quiet, constant, and still not finished teaching us what it really is.